So good afternoon to everybody. I think we can start now. If there is a problem, please tell me. Are you okay with the voice and with the figure, etc.? I am very happy to chair this last session of this Festschrift dedicated to Professor Ruffini, to his 80th anniversary, because we met with him 25 years ago. At the time I was a new PhD, still a shy PhD, just returned from France to my country, Albania. And it was in fact an email I sent to him concerning a paper on boson stars. I was trying to publish the paper in a review where Professor Ruffini was one of the editors, and I had chosen to contact him because his well-known paper on boson stars, and also for the reason that he is Italian, and Italy is the closest country for us, for Albanian, outside Western Balkans. And his answer was really very enthusiastic. He was surprised and happy that there were at least one astrophysicist in Albania, a small country. Since our exchanges and cooperation keep growing, and we hope that soon Albania be a country member of ICRANET due to extraordinary perseverance of Professor Ruffini. These days, in this Festschrift, we saw flowing several subjects of relativity and astrophysics in a background of an entire and vast universe, subjects that Professor Ruffini brilliantly dedicated his own life. And these subjects I felt they flowed like a wind, maybe that wind of Giacomo Leopardi, the well-known Italian poet of the infinity. I have some verses of him. E come il vento odo stormir tra queste piante, io quello infinito silenzio a questa voce vo comparando. And I would like to say happy birthday to Remo. And let's start with our new speaker, Professor She-Sheng Xue. Its floor is for you, Professor She-Sheng Xue. 50 minutes, please.
Hello?
Professor Xue, She-Sheng Xue.
Yes, okay.
You share a
yeah. Okay, hello everybody, good afternoon. I'm present this talk to dedicate to the birthday of the Professor Ruffini. Can you see my screen?
Yes.
Okay, good.
Here.
To dedicate to the Professor Ruffini 80th birthday of 80 years old. And for many reasons which has been said by many other speakers. But I stress the reason I want to for it on the scientific, which is in this talk I present a fundamental theory which accommodates 4 types of dark matter particles from the point of view of the fundamental theory of the elementary particle physics. 4 types of dark matter particle. 2 of them actually has been studied to explain the phenomenon in astrophysics or cosmology by Professor Ruffini. One is the sterile neutrino. In his way, he called the fermionic type particle, and Ruffini calls i-Eiso. He tried to use it to explain the structure of the galaxy size, the object like galaxy. The other one, the second one is axion. which is pseudo-scalar particle. In fact, it's extremely light. In fact, Ruffini has used this as a candidate for extremely light boson-like particle to explain something in supergalactic, and for his well-known paper. So this paper, instead of astrophysics cosmology, I try to accommodate these 4 types of dark matter particle in a fundamental theory of the particle physics. And this paper is just appeared this month, this week. So I take this chance to briefly present what's the idea of this paper. So this paper is concerning a particle axion, and which historically is Peccei-Quinn theory. And I try to take a Wikipedia to explain, to give you an idea what's about this story. The story is the so successful QCD Lagrangian theory, that it permits a term, you see, theta term, which is remoralizable and fulfill the gauge symmetry and all other fundamental principles as fundamental theory. However, it is by the CP symmetry, charge and parity symmetry. So it looks very nice. Everything from the theoretical part, this has to be there, theta term. However, from the experimental point of view, this term should not be there because QCD process has there's not anything observed via the CP symmetry, charge and parity symmetry. And besides, the other important fact is this term will contribute a neutron electrical dipole moment, which observed is extremely small, proportional to this the coefficient with theta term. So instead of the consistent with the experiment, though the theory from theory part is so elegant, the theta term, theta parameter has to be extremely small, unphysically small. So this is what it means that the beautiful principle has a problem with the observation. So this called strong CP problem. Then how this been solved? This come to Peccei-Quinn. The Peccei-Quinn has a great idea, departed from the nice theoretical, inspired logical. He said this theta term actually in the Lagrangian is come from a broken of a global symmetry, here called a Peccei-Quinn symmetry, U1 symmetry, like this one. Once this is broken, the Gordon theorem tells us there's a massless particle, they call QCD axion, going around. And this symmetry will guarantee you that this axion mass is so small, which means theta very small, and it will be the solution, theoretical solution to the strong CP problem. But then this axion has been proposed. They have problem is we never have observed such actions, reality until today. The others I will mention, the theory proposed by Peccei-Quinn, they have another problem with the experiment. They predict a process related to the axion they predict. However, again, the experiment falsify what they propose. So this has been a problem for several decades. Now, so then what's this Peccei-Quinn theory? They introduce this symmetry, okay, I just say U1 global symmetry associated with the quark field, okay? Then they found very nicely, everything worked, but however, they predict something associated with process with the quark, has not been observed. So here instead, instead of quark field, here I associate this symmetry to the sterilized neutrino, the right-hand neutrino, because as I will explain later, right-hand neutrino has to be a candidate, has to be a component in a standard model of particle physics. But before doing so, I forgot to say that some people try to generalize this Peccei-Quinn theory by introduce actual quark field. It's not really quark, but much heavier than quark, to associate this Peccei-Quinn symmetry to solve the problem of Peccei-Quinn, which I just explained. It's not consistent with experiment. So, because Peccei-Quinn used the quark field to associate this symmetry, their symmetry is failed. Someone introduced the very heavy quark, is a hypothesis quark, to associate this symmetry, and this quark is so heavy, that's why you don't produce the process like a Peccei-Quinn symmetry with a quark. But here instead, okay, this also has been past 40 years for this. Here, instead of this heavy quark, which is suppose heavy quark, here I use sterilized neutrino, okay, to associate this Peccei-Quinn symmetry of U1. And this sterile neutrino has been already candidate for in the standard model. Low is no gauge. Low is no gauge. So we have we know the standard model of the particle physics. We have three family of neutrino, left-handed, and then the problem of neutrino mass and oscillations, and people expect there are another three sterile neutrino. Here in the equation 2.1, another three sterile neutrino for three family are in the particle spectrum. So how these three particles sterile neutrino come to the game, then we need to have a theory of motivation in a very high energy. So in very high energy, let's say in a Planck scale, for example, you have a quantum gravity, all this form theory, and there's a regularization. So one of the strong mathematical theorems tell us the Lagrangian has to be four fermion interacting, okay? And the one which I wrote is actually come from the other part, from the other point of view, is torsion free of Einstein-Cartan Lagrangian, okay? Once we have this Lagrangian, we write this Lagrangian to satisfy the standard model gauge symmetry. They are same for all the quark and leptons. But here, for this talk, what I need is for top quark channel and sterilized neutrino channel. For top quark channel, this four fermion interacting. Then we ask what's dynamic of this four fermion interacting? We need to answer where is a scaling node, where is a fixed point, how is remodelization group, and to follow. So it's not enough just write Lagrangian. We need to redefine where interaction is, how is it go with the scale energy. So here there's a two interacting point. I won't go to detail, but I want to just tell you the main idea. 2.2 is the one for the top quark channel. The 2.3 is the one for sterile neutrino channel. And we are very focused this 2.3. The 2.1 top quark channel actually is giving the Higgs phenomena, like Lampuion asenia, like this Higgs mechanism, like this like in condensed matter of the low hyperconductivity, this phenomenon. Okay, spontaneous symmetry breaking, the fermion get mass, and Higgs particle produced. Beside, there is a Goldstone mode become a longitudinal mode of the part of the WG boson. Okay, then now today we know the Higgs of a mass of Higgs particle and then the top particle. We can completely fix this curve of the standard model of physics in standard model physics. So now we come to the sterilized sector for sterile neutrino. The same story happens. We have a spontaneous symmetry breaking of the sterile neutrino of the Peccei-Quinn symmetry, and we have a two particle produced. One is this Goldstone mode, which actually is axion. The other is a scalar particle, which is like a Higgs particle. So we can follow the same thing. We have a Lagrangian for the sterilized particle, which predict the interacting and the mass spectrum. So here you see this, the breaking is the same as Higgs mechanism, 246 GeV. And Majorana sterile neutrino has a has a mass. Okay, heaviest one is 10 to 2 GeV. And this Higgs type of sterilized particle, chi, is a 10 to 2 GeV candidate. And besides, there's axion. Axion is like a Goldstone mode, but it's still going around without becoming the longitudinal mode of the W boson, because he has no coupling to W boson. That's why he turned out to be a candidate of axion, naturally, not with by hand. And for sterile neutrino, they build this spontaneous symmetry breaking can give Majorana mass, direct mass, and by the mixing, we give this sterile neutrino mass. So sterile neutrino mass has three possibility. Heaviest one, lightest one. The lightest one, recently, we are collaborating in Iran. We saw lightest one has contribution to Xenon physics.
Professor,
been very good.
Accelerate a little bit, please.
So then actually axion also has interacting with normal particle, 6.1. So by this idea, we can see this axion particle has a coupling, very weak coupling to the standard multi-particle gauge bosons. Okay, then by this we follow the normal standard calculation. Okay, here is for Xenon fix, we fix what this coupling is. And we follow the standard calculation to see what's the Peccei-Quinn in this settled in this issue of the sterile neutrino, and compare with all other theory. The Peccei-Quinn has problem with experiment, and then so-called generalized Peccei-Quinn theory, so-called these two type of theory is, as I said, they used to some assume heavy quark of the very high mass of the 10 to 11 GeV to try to avoid to contribute with experiment. Instead, I'm using this sterile neutrino. I'm using actually sterile neutrino, which already in a standard model, which must also process U1 symmetry, and which can be exactly the Peccei-Quinn symmetry. So by this idea, we follow the calculation, okay, the standard model calculation, we get result present by this group, okay. Here, there are so many experimental on the ground to test this axion particle, not only on the ground, but also on the sky, astrophysics bound, because if this particle presents interacting, He must follow all observation. So there's this prop is the coupling of the action between the photons and axion masses. So there are many experiments that exclude many regimes, like supernova, whatever. Okay, so the yellow line is a QCD action predicted by Peccei-Quinn. Okay, and the origin line is sterile QCD action. Is down here, and in the future, in near future, there is the very scientific experiment. This one, but will reach the regime which I say the action, sterile neutrino action should be laid. Okay, this is zoom. This is zoom. This is QCD action. This is actual action I predict. This is where experimenter can reach, and all this. In the sense of astrophysics cosmology, there also people detect to exclude what it can be for the actual mass and coupling. Okay, this is final result of my framework. And here I give all the limit, upper limit of the all coupling, all the possible coupling upper limit. In fact, the conclusion for experiment is, according to this, there are no recent experiment can reach this.
Professor,
means you are not able to see the action.
Sorry.
Chi boson. Sorry, I'm finished.
Okay, thank you.
In fact, connecting the Ruffini's this superride scalar boson, the action is a candidate, which are extremely small. Here I give limit 10 to minus 8 electron volt. I think it's 10 to minus 18 electron volt, which can perfectly explain the explaining this supergalactic scale phenomenon of clustering or this type of phenomena in astrophysics. But from the other hand, I stretch again, in near future, the experiment of this very scientific experiment will reach the regime which I predict. This. Thank you for your attention.
Thank you very much, Professor Xue, for sharing with us your contribution on dark matter. And maybe there is any question. Let me. Okay. Thank you again. Let's move to our next speaker of this afternoon session. It's Christian Cherubini. Professor Xue, may you...
I need to, how do I...
Yes, you can free our screen.
How?
Share, maybe.
Can someone can, I need to stop sharing.
Stop sharing, so... Okay, it's excellent. Thank you very much.
Thank you.
Thank you. So, Christian?
Okay.
Okay, the floor is to you.
Thanks. So, can you share? Okay. Can you see it?
Yes, it's okay.
Thank you very much. Okay, thank you. I'm gonna talk about magnetohydrodynamics around the Kerr black hole. This is a work in collaboration with Simonetta Filippi, Alessandro Loppini, Rahim Moradi, Remo Ruffini, Wang Yu, and She-Sheng Xue. But before entering into the details, I would like to use some time to say something in relation to this beautiful conference that we are having right now for celebrating Professor Ruffini's birthday, 80th birthday. And my starting point is this joke that I have heard several years ago in England. Essentially, general relativity, in general relativity, there are three major tribes: the Wheelerians from John Wheeler, the Zeldovicians from Zeldovich, and the Shamanics from Sham. And I have to say that in these almost 25 years of collaboration with Remo Ruffini, going around the world, I've had the unique opportunity to recognize and appreciate and absorb most of these points of view. But with him, I had also an additional flavor coming from the Fermi school and also from the Landau's one that I experienced in his research team. And in addition, I have to say that during the several Mersel-Grossman meetings all around the planet, the world, I had the possibility to appreciate in a total wide range way the peculiarities of all the other families, all the other GR communities of the rest of the world. And so I would like to deeply thank Remo Ruffini today here for all he has done for GR, for astrophysics, relativistic astrophysics, in more than 50 years of activity. Okay, this talk is essentially based on this literature, the classical papers by Ruffini and Wilson of 75 and Tipo d'Amour of the same year, an article of 2000, so 25 years later, by Chris Doran, and this publication we produced some years ago, which summarizes what you're going to see right now. The talk is organized in this way. We have a review of those 75 works. Then we introduce this type of coordinates, which are horizon penetrating. I have to say that we have used with Professor Ruffini some years ago these coordinates also when we introduced and studied the Diedo torus in another article you can see there. Then we're going to revisit the solution and have a physical discussion, and then we're going to give some conclusion. The starting point is that the problem of Kerr black hole was solved by Tucholsky in '73 via his masterpiece Tucholsky master equation. But this equation, to be solved and studied, has got some drawbacks. There are special functions required because this is an eigenvalue problem. You need numerical tools, and you need essentially to study the Fourier Laplace problem, apart the recent contribution in numerical relativity. So in this framework, analytical solutions of simpler form, which have physical relevance, have been useful in order not to have to deal with all these mathematical problems. And to my knowledge, the most famous ones are the Wald field, 74. This is an electrovacuum test field solution of Maxwell equation, and it uses the Killing vectors to produce at cost zero exact solution of specific exact solutions of electromagnetism in Kerr background. This is the Papa-Pedro fields theory, and also the classical work by Ruffini, Wilson, and D'Amour, which instead deals with MHD and is based on geodesics. So, starting point, let's find analytical solution for this test field in GRMHD, as we said. In their articles, 75 articles, the Kerr solution was studied in the Boyer-Lindquist coordinates. This is well known. Then one sets up Maxwell equations with sources and has several assumptions which allow then us to get analytical solution. The first one is a perfect plasma with infinite conductivity. Then pressure is neglected with dust, and we neglect magnetic force terms, the first term. Then fluid motion is given by geodesics, essentially. Moreover, other assumptions on the for velocity on the geodesics is given. This is the case. With this choice, u theta is a constant of motion, and this is the vector field component. These are the vector field components. Then one requires, moreover, overall neutral stationarity, axisymmetry. This allows us to have only one component of the Maxwell vector potential, and then one can reconstruct all the Maxwell field terms. and inserting into the relevant equations of the tube, one at the end is able to get analytical solutions in terms of this type of integrals. Then, once one gets the Maxwell field, one can insert that in Maxwell equations and get the forecurrent. From forecurrent, one can cut in t-equal constant slices the system, and through a specific normal, you can build up the magnetosphere charge. Induced metric, this is standard. Now, by using Gauss theorem and remembering that we require a global neutrality, we can say that the Q of the black hole must be minus the Q of the magnetosphere. This was a mechanism to produce charge on the black hole. And in their article, in order to induce a net charge on the black hole, Ruffini and Wilson had a specific assumption of U theta, which has this behavior, different behavior in the two M-planes, okay? And you see here a constant is assumed, and then you can have quite simple Maxwell invariants, in particular E dot B is 0, and B square minus E square must be larger or equal to 0. Additional simplifications were inserted in those articles. In particular, U theta must be taken equal to 0, so this is not the case. Okay, this is the case, the new case. This means that A phi is a function of theta only, and it's chosen in that article in this way, is a modulus of cos theta times a certain constant. Now, this is the 75 theory. We are able to see what happens by using a tool which was introduced 25 years later. These are horizon penetrating coordinates, and they occur naturally in analog gravity, essentially acoustic black holes, and are extremely useful in numerical relativity too for the problem of excision. The idea is that you can continue the code well in these coordinates, well inside the black hole, the event horizon, and if something strange happens there, it cannot escape because it's confined well inside. Essentially, the light cones point towards the singularity, and so nothing strange can happen. This is a very important tool adopted nowadays. Then one has to pass from Boyer-Lindquist to this Doran. I call them Doran-Pellevé-Boutstrand-like because in the case of Schwarzschild and Resser Nostrum, they were introduced by Pellevé-Boutstrand, so I call them DPG. This is the coordinate transformation, which has new variables in terms of ones. You see T capital, Phi capital, R capital, theta capital. Then you perform all the steps you need. You see that the new line element is a little bit more complicated. It has got some more of diagonal terms in comparison to the Boyer-Lindquist case. And then it's useful to redenote capital R with small r and capital theta with small theta. Hello?
You know that one very likely is Monet.
Okay. Then we can have the transform vector potential that you can see in these new coordinates, the transform for velocity. So essentially, we are rephrasing everything in this new coordinate set introduced 25 years later. If you choose U theta equal to 0, the for velocity becomes quite simple. Here, this is the t-equal constant normal to the observer, and T capital is the local proper time of observers in free fall along trajectories of constant theta and phi starting at rest. This is the interpretation of these new things. In these coordinates, there is one component only for this solution, for the Maxwell tensor. The Maxwell invariants are nice, compact. This is the ISO level plot of these Maxwell invariants. Then one can use an orthonormal local Lorentz frame to see what happens. And in this frame, he discovers that only one component of the magnetic field is measured, is distinct. So here physics comes because we know that the electric field is zero everywhere, and this was expected from the initial condition of perfect plasma. But the other point is that usually from non-relativistic plasma physics, even, this is the simple case, is well known that there must be a frame in which this plasma, in which charge for this plasma, charge density must be zero everywhere. The problem is that usually it's very difficult to find this frame explicitly. In this way, instead, we can show this, that we did it with this theory. This is the for current, and as you can see in these new coordinates, there is not the zero component. These are the other components. This delta comes from the modulus. You have this problem when you make derivatives and so on. And then one can compare what happens to the current lines, the electric current lines, for the same system. This is an extreme black hole in both cases. This is what happens in the old view, which was the Boyer-Lindquist one. You see there is the event horizon. Nothing can enter inside because the event horizon is, well, the coordinates are singular there. And everything is wheeled, wheels around, no? The event horizon. You see in blue, you have something strange because on the equator you have some problem comes from the modulus. You can fix that. Instead, this is what happens when you are in free fall with the plasma. When you are in free fall with the plasma in that frame and those coordinates, you see that there is no twist, and you enter well inside the event horizon. So essentially, this is what you see if you're falling with the plasma. Other things that we must check. We must check that charge density is zero, but this is the case. And if you project the forecurrent for that velocity, you see that rho is zero everywhere for this observer. So essentially, this observer doesn't see electric charge density, no electric field, and measures a non-vanishing magnetic one. So in summary, we are naturally measuring everything by sitting on the plasma. We are in the commoving plasma frame, and using this theory of the 75 rephrased, we have found explicitly this frame. It's nice also to study the electromagnetic energy, which is stored outside the event horizon for a certain slice, t-equal constant slice, in between two radii from the horizon to a certain radius, and the formula for the energetics of the systems are very nice. What remains, last slide, remains this point, which was the case of the induced net charge on the black hole. In their article, Ruffini and Wilson assumed that, but then there and also here we use the case instead in which that constant was zero. And to study this additional case, one should use different coordinates in comparison to the Doron one, because the Doron one belongs to the case in which that constant is zero. So this should be adapted in somehow, and this is the idea for the future, to extend and to find new coordinates to study this type of things. But the conclusion that I would like to give at this point is that it's extremely useful to revisit old problems by using new tools which were developed many years later. I mean, Ruffini, Wilson, and our work happened in the heroic age of the black holes, 75, 70, 80s, since the last 60s. But it's useful to use modern to revisit them and see if something new comes out. Thank you.
Thank you very much. Thank you very much, Christian, for this beautiful recalling so many fundamental work. And of course, right now we are very, very interested to come back to this after having introduced the effective charge due to also thanks to your work of the gravitomagnetic of the Kerr metric plus a magnetic field. And it's a generalization of all the work we did together on the diadotos and so forth, which now finally has become part of the building of the inner engine of GRB. And thank you for your traditional contribution on that, and look forward to collaborate with you further. And thank you for this present for my anniversary. It's one of the best presents I received.
Thank you.
Say hello to Simonetta as well.
Thank you.
Thank you, Cristiano. Maybe there is another discussion or question. Okay, if not, let's move to our next speaker of this session, Dr. Donato Bini.
Yes.
Donato, okay.
Thank you. Let me try to share screen now. Can you see my screen?
Yes, it's okay.
Okay. Okay, so the topic of my talk concerns hyperbolic encounters in a two-body system and is based mainly on a series of works I did in the last few years in collaboration with Thibaut Damour and Andrea Geralico. This field is another field pioneered by original works by Ruffini. And this is perhaps not very well known. I myself discovered this not so many years ago, but in the 70s, in what Christians termed the golden age, Ruffini and Wheeler already studied the problem of hyperbolic motion of a two-body system and the consequent emission of gravitational radiation. In the simplest approximation case, which is called the splash radiation. But I must admit that all the basic tools and also the underlying difficulties to solve this problem at higher post-Newtonian approximation orders as is done today were already contained in their original work. So it's my pleasure to talk about this splash radiation and the way in which we have extended at higher PN orders. Indeed, we revisited this problem in 2017 when we studied the gravitational scattering of two black holes at the fourth post-Newtonian level of approximation with Thibaut Damour. And then later, in last year, when we developed the frequency domain analysis of the gravitational wave energy loss in this hyperbolic-like motion situation with Andrea Geralico. Let's briefly set up the problem. We have a two-body system. We look at it in the center of mass system. We assume the two bodies and then the relative motion is hyperbolic-like. We use post-Newtonian approximation. We use harmonic coordinates. The motion is parameterized in a standard way using the so-called Damour-Deruel approximation or parametrization of the orbit. You see here the radius, the time coordinate, and the azimuthal coordinate are expressed in terms of a new variable, this b, which ranges from -infinity to +infinity, and the orbit at the Newtonian level is an hyperbola, and let's say hyperbolic-like a higher PN order. All these orbital elements have a post-Newtonian expansion, here truncated at the second post-Newtonian level, and eta is an indicator for the inverse of the speed of light, which is used in standard post-Newtonian approximation. So what we do? We would like to compute the total radiated energy at a certain high PN level, let's say 2 PN, because this was the limitation of the work I'm just reconsidering here. So we have to integrate the flux, but the flux bears some instantaneous contributions due to the multipolar moments of the system, which are the electric quadrupole, Then there is the electric octupole, the electric hexadecapole, the magnetic quadrupole, and the magnetic octupole. All these are functions of the orbit, are evaluated as a function of time, and then integrated all over the time from -infinity to +infinity. In principle, this is an easy task. One can simply pass to the Fourier domain for convenience, and then cast the problem in the form of integration over the spectrum of the frequencies. And there is this kernel here, which has the same contribution I mentioned above. And that's it. Just perform the integration and it's done. Let's look at this kernel. This kernel takes contribution from the Newtonian level, the 1pn, 2pn, etc. And at the Newtonian level is a function which involves Bessel K function of a certain order, depending on this variable u, which is the frequency, roughly, rescaled frequency. But what is the problem? The problem is that this index, the order of the Bessel function, depends on u. So you have the integration variables, both in the argument of the Bessel K function and in the order of the Bessel K function. So this, which was initially so simple problem to postulate, to write, seems to have a very difficult solution, because the dependence of the Bessel K function on the integration variable in the order. So what to do? The idea of Thibaut d'Amour was just expand in large eccentricity. Remember that this P was U, the frequencies, divided by ER, the radial eccentricity. So when you take ER going to infinity, you get to 0. Indeed, then the problem is just to find an expression for the derivative of the Bessel K function with respect to the order, as much as you can go beyond the 0 order level. So the leading order level is okay, because there are no problems with these derivatives. And this is exactly the Ruffini and Wheeler splash radiation contributions. But now the problem is to look for the higher derivative of the Bessel K functions with respect to the order. So the splash radiation gives this kernel, which can be integrated, and one can go in the expansion at high eccentricity as much as one wants. But the problem is that beyond the splash radiation, there are the difficulties I was mentioning. And the difficulties are still around because nobody knows higher derivatives of the Bessel function with respect to the order beyond the second order. There are attempts, but in the scientific papers published, this is the level we are. And using this second order derivative with respect to the order is not an easy task, because you have the gamma function, hypergeometric, Meyer G functions. So even if you give to any machine this expression and then you hope to perform an integration by using this formula, it's more or less hopeless. So we use the other tricks. We exchange the integrations, order and derivatives, and we succeeded in obtaining up to the second PN order and up to the next to leading order in the expansion in high eccentricity, the results at 1 PN and at 2 PN, which you read here, using also other integral transform like the Melling transform, but these are details I don't want to discuss. The final result reads this way, and it's the generalization of Ruffini's and Wheeler splash radiation at 2 PN. Of course, working in the time domain sometimes simplifies things, And indeed, at 2pn, one can get in the time domain a full analytic result, which is consistent with the previous one in the frequency domain. But it's better to have at disposal both tools, because in some example, one is more convenient than the other.
All consistent, full difficulties.
Sorry?
No, I was just reading you.
Okay. Now, the problem is that the integrals involved are very large expressions, and one needs often to integrate numerically with high precision. High precision means hundreds of digits, and then reconstruct the results by using interpolating techniques like the PSLQ algorithm. And we could accomplish this result by working with high energy people like Stefano Laporta and Pierpaolo Mastrolia. So for the loss of the angular momentum and the energy and the linear momentum of the system, things are more or less the same as I was showing, but this is not the case, because beyond the 2.5 pn level of approximation, one needs to add to the instantaneous contributions the so-called hereditary terms, which are called tail, tail of tail, tail square, etc. And this depend on the past history of the system, so are not local contributions. One can compute this only in the Fourier domain, and here I sketched the level where things had, and we cannot go much beyond, in the sense that the instantaneous contribution to the losses of energy, angular momentum, and linear momentum up to now are at 2, or in some case, the energy at 3 pn. The tails are only at the fractional accuracy level of 1 pn. That's it. We use this information after playing with certain symmetries to build the Hamiltonian, the conservative Hamiltonian of the two-body system up to the 6 pn level in a series of papers of a couple of years ago, which involves, however, a certain number of unknown parameters, 2 at 5 pn and 4 more at 6 pn. So for the moment, the status of the art is to have 6 unknowns, but the big effort has been that, for instance, at 5 pn, among 97 possible coefficients, we have determined 95 of them. Instead, at 6 pn, we have determined 147 terms of the 151 total number. So these things are really useful. And in our contributions, which is, I'm going to finish soon, we never include a square of radiation reaction effects, because these terms really do not exist yet in the literature, but they are at the level of challenging for future work in this field. Let me say that the true hyperbolic encounter in my scientific career is the one with the Professor Ruffini. I have been often scattered, that means literally sent by him, his decision taken in 1 minute, and sometimes completed by phone, including buying the flight tickets to meet and collaborate with Bob Janssen, Baram Mashun, Thibaut Damour, to discuss with other scientists like Volodya Belinsky, Jürgen Lernertz, Roy Kerr, etc. I entered this group long ago, 1987. So here you have a family photo taken from the archive of Dr. Bob, where you can see people passing through the G9 group over the years. Then thanks for your kind attention. Happy birthday, Professor Ruffini, and thanks for continuous encouragement and all the generous support for me all over these years. Thank you for your kind attention.
Thank you very much, Donato. However, I have to be frank. I am reconsidering all this work that you are doing with Thibault on the ground of a discussion I had with Nathalie de Ruel. And if I have to tell you the truth, I am extremely concerned, not about the mathematics, but about the physics. In other words, what the LIGO people have done is to develop a very sophisticated way to solve the field equation of a system of particles emitting gravitational waves. The most simple example was LIGO with the two binary of the first event. They compute the binary to some approximation, and then they compute the gravitational wave emitted. The point is that they look only to the gravitational wave emission. This is the problem. You understand what is the problem? No?
Yes, I understand. One should complete this work by looking for electromagnetic counterparts of energy.
No, excuse me, no. You don't complete that work. You don't complete that work. You are doing already, like LIGO people have done that work already. Namely, you look either for a two particle following Landau-Lifshitz, or better still, if you want to implement the sterile approach, which I did with the people sterile, you make better equation of motion, or now you make even better equation of motion following Thibault d'Amour, and then with the PPN, and then you go even further to a higher degree, still with PPN or with one body, you understand? And you compute the gravitational wave emission. And then you check this gravitational wave emission with the people in Germany, which they feel the trajectory which fits better. I have to say that this is a total nonsense, because by the moment that you impose gravitational waves, okay? There is only one solution, which is that one, but by definition, you cannot observe it, by definition, because it emits only gravitational wave. You understand? It emits only gravitational wave. Therefore, by definition, you cannot observe with any electromagnetic radiation or anything. Therefore, the splash radiation I consider with Wheeler, following the gracious work of his teacher, Niels Bohr, tells that you emit that gravitational wave, but you cannot use for anything, because it tells you that you are only seeing gravitational waves. It's a locked system. And if by any chance, listen, if by any chance you would like to implement with an electromagnetic radiation as well, there you finish your game, because the solution with another interaction change completely the geodesics. Completely the geodesics. Therefore, you have no right to use this geodesics. you will never find anything. You will never find anything because by definition, you cannot emit in your system anything else than gravitational waves. And if you interact in another way, you are lost because all this work is bullshit. It's not helpful. It's like if you take a Cramer equation, okay? Hai ragione, devo stare calmo. It's like if you use Cramer work and you try to solve gravitational wave from Cramer work. It's absurd for the binary pools. They order me not to speak longer, but I have to say, and I will discuss with Sipira calmly, I cannot speak more than this point of this tragedy. I mean, the point on gravitation. In the entire book, there is no room for electrodynamics from vacuum polarization. There is no place for physics. Therefore, he wanted to obtain a lot of gravitational waves. And then he used whatever was in the book, the black hole of Kerr, the Zerilli work. Then he forgot to mention Zerilli because Zerilli was author with me of a paper against Misner. Therefore, Zerilli has disappeared from the book. Stiomno, one of the finest scientists in my life, Stiomno, was also cancelled from gravitation. This is incredible, but it's no problem. The book is good for gravity. Now, the folly of this man has been to, since he wanted to have gravitational waves and black holes, okay, is to use only gravitational interaction only to find black holes and gravitational waves. But you cannot do it. Because by definition, you go in a system which cannot radiate anything else than gravitational waves. If you want to radiate a little bit of electromagnetic radiation, you are sunk. Because all the work you have done, you are doing the PPN, the 3PPN, is worthless. It's worthless because it's enough a small charge of one of these objects that destroy all the work you have done. Destroy all the work you have done. I hope you should be aware of this tragedy, and I will conclude on this today. But you gave me a good occasion, and I hope that Thibault is an extremely sophisticated mathematician, but all the work we did together, I guided him as a scientist, as a physicist. The only work he did not do with me is this one of this PPN and so forth, which is nonsense from the astrophysics point of view. Because you are locked in a system, and they found a system, I hope you got to the point, they found the system which fits a system which emits only gravitational. It's absurd. If you consider binary pools, of course, it's total nonsense. Or whatever interaction, even not the binary pools, even if you have a magnetic field on a neutron star, you are lost. Because you are imposing to be only on gravitational waves. Therefore, these solutions are meaningless from an astrophysics point of view. And they can be implemented only on two cases. One is that they are using them to inject the solution, which they did many times. Or second, they cannot find anything, like they are not finding, because nature does not follow absolutely just gravity. only the book Gravitation of Professor Thorne follows gravity only. And I remember when Dimitrios went to Caltech, after a few months that he was there, he called me up. He said, this man is crazy. What do you mean? Is crazy. He's crazy, Dimitrios told me, because he considers only gravity points. Sorry to tell you that, but it was, I feel much more comfortable to have explained to you before explaining to anybody else. Okay, Donato, we
Thank
keep
you.
It's insane. This man is insane.
Okay, thank you, Donato. Let's move to our next speaker, Manuel Malheiro. Minutes, please. Manuel, please.
Sorry, are you listening? No. Yeah? Okay? Are you okay or no? Yeah.
Yes,
Okay,
well, you are okay. If you
okay,
have
so let me see if I can share my screen
yeah.
now. Here. Share. Let's see if it comes. Appears now. Here. It's okay.
It's fine. Yes.
Let me see if it opens. Not open.
Okay, we see.
Now it's okay. Okay. So are you seeing and listening well? Yeah.
Excellently.
Okay, good. So first, it's very happy to be here from Brazil, participating in this important and I don't know, very friendly meeting of Professor Ruffini, 8 years, his birthday. I will talk about this work, structure and stability of massive hot white dwarfs. It's a work my PhD student Sylvia did and just finished her thesis end of last year. And I collaborate with Professor Arbanil from Peru, a specialist in radio oscillations. And but before beginning my talk, I'd like to just say some words to Remo and of course to all of you. So ICRANET has of course strong collaboration with Brazil. I never met Remo before 2010. I went there in Rome, I think it was 2009, and talked with him that I would like to spend my 1 year, a sabbatical year with him, and he was very open to that. Okay, I was surprised because I never met him, and in fact I worked more with neutron stars, quark stars, and things like that. And but he really said, "No, come, it's very good. It will be very interesting for us." And so I went with my family and spent 1 year essentially 2011 there, and did this work that I show here for you, this alternative model for magnetars, seeing them as very fast and magnetic white dwarfs. And I remember when I don't know, I realized that the white dwarfs could spin only around, have periods at least around 1 second of period, and so could not spin too fast. And these magnetars, all them have like 10 seconds. So I thought that, oh, maybe they are really very fast rotation sources and not slow as they are if they were neutron stars. So I come to Remo with these ideas and he liked it. So I stayed doing this work, changing essentially the scales of the problem with the moment of inertia, radius, larger, of course, now like 3,000 kilometers and not 10 kilometers of radius for neutron star and so on. And so I show all of that, and he invited Jorge to come to join this work. And George comes and said, oh, but this was done by Paczynski much before, and I didn't know that. And of course, I was happy because everything I have to do was there already. But I should say that I was really impressed that Professor Remo always like to challenge this magnetar model, okay, and this concept of some energy, magnetic energy that is really the source of this luminosity, and in the white dwarf model don't need that more because we have much more rotational energy now lost because of—
And a lot of moment inertia.
Yeah, a lot of moment of inertia. And of course, this work that has already 1,000 citations is still still heretic, okay, in some sense, that many people—
You said we got 1,000 citation?
Yes, around 1,000, yeah.
Incredible. You've chosen a good topic to join.
So I'm saying is that one thing that I should say, against all the community, against all the referees, because we tried to put this paper on Science at the beginning and after Astrophysical Journal, but only the Japanese people were open because they already a very fast magnetic white dwarf at that time was A Aquarius that already showed.
But I can tell you an anecdote. Why I choose Japan?
I don't know. I thought that maybe you know that they will be open. I don't know.
No, but I tell you why. I tell you why.
Mm-hmm.
Last period of Fermi life,
mm-hmm.
he submitted a paper about the statistic of high energy collision.
Mm-hmm.
And the US, they did not want to accept in APJ, in PhysRev, Fermi paper, which is one of the most beautiful paper of Fermi about high energy collision.
Mm-hmm.
And then I looked where he published such a controversial paper. By the way, people against that were big shot, including Gelman, because if Fermi was correct, there was no hope for his alternative theory, which of course was a good reason, but was not a good reason to shout, to not allow Fermi to work. And we discussed this in the next floor with Gelman when he came. Was not a good reason not to allow him to publish that beautiful work. And then Fermi chose Japan. A second publication in Japan. And I kept that in mind. Whenever we
I didn't know that.
an ideological problem in Europe or whatever, let's go to Japan because they are good physicists there and they can appreciate good physics. And we did to Japan, and now we have 1,000 citations.
Yeah, and yeah, so I didn't know that. Oh, very good, very good. Always learning. Yeah. So I must say one thing, because as we wrote here in this abstract, that we will need more missions and more results and more observations to really go further on this. And the one thing very interesting that maybe I think Remo is aware, okay, but maybe not all of you are aware, is that recently, after 2018, okay, with this ZTF facility, this Zwicky transient facility of Caltech at Palomar Telescope Observatory, they are finding several fast white dwarfs.
Yes.
And now for the first time, because always when I gave this talk in many conferences, even in this big one of, I don't know, I was in Berlin, no, I don't know what is the name, but okay, it doesn't matter. Always people, in some sense, change a little bit the face, because all the fast white dwarfs that were found until this paper were in binary systems, okay, always. And we, of course, know that magnetars are isolated stars. And we propose that these isolated white dwarfs, fast ones, would really come from mergers of double white dwarfs. But at that time, we have no such white dwarfs. Now, we have one pulsar of white dwarf that is in a binary system, it's true, IR Scorpius, but you have now a white dwarf with 70 seconds of period, isolated, smaller than the moon, around 2,400 kilometers, and a mass of 1.3 solar mass, 1.32. And they found another one, and they have much more, as they say in this Nature paper of 2021 or 2. I remember, like 21, I believe. So, the missing link that was fast and isolated and magnetic, these are also very magnetic, 10 to 9 Gausses, and this model of white dwarfs needs white dwarfs with 10 to 9, 10 to 10 Gausses. And so they don't exist, but now they exist. And so they are here. And maybe some of them collapse to a neutron star that are the magnetars. That is what I'm working now with Jorge Rueda and Remo. Okay, so maybe some of them are fast white dwarfs, and the others are neutron stars that come not from supernova explosions, but for collapse of a very fast magnetic white dwarf that is a product of this white dwarf merger. So I don't know. I'm to say that you need to believe on the things and waiting for the results. And so this is some good history that I would like to put here. And of course, I've already talked, I think, all my time, but let me show you only one thing. So this motivation to do this structural stability, see, of massive hot white dwarfs, massive. That is what we have investigated here, okay? Because these very massive white dwarfs, they have surface gravity higher than 10 to 9, okay? Meters per centimeter square, okay? So essentially are very massive and very small, okay? So we follow, okay? So one thing interesting is that general relativity, and this I should say that this is a paper I did with G. Anderson and Marinho in ITA, but I should say also that this result was already seen in the works that Rueda and Ruffini and Rotondo did, but was not really so maybe stressed, is that nowadays, no one can do massive white dwarfs with more masses above 1.3 solar masses without general relativity. So the idea that is in the books, that you don't need general relativity to study white dwarfs, is only correct if you are with masses below 1.3. So Chandrasekhar white dwarfs, they need general relativity. Why? Because the radius of the star is much smaller. It's like 50% smaller than would be if you do Newtonian physics. And this was important now in this work, because in this work, we compare the results with the previous results, okay? And what comes the difference, essentially, was that the radius was wrong. And so G is the same because they measured the G. The radius is smaller, the mass is smaller. And so this is essentially the message of this work I'm going to present you. Of course, I think I have I don't know how much time I have because when I began, I don't know.
I think
I keep going, okay. Okay, so I will keep going. So what we did,
not too long.
Okay, not too long, yeah. But what we did, we essentially deduce, of course, remember, have other important papers that analyze temperature in white dwarfs. The first one, 2014, with Cesar Carvalho, was a former master student of me that went to ICRANET and was advised by Rueda and Remo. And so they did already this temperature for white dwarfs with masses below 1 solar masses, essentially. Okay? Boskayev, after in 2019 and 2018, also studied rotation, include temperature. And so this is, in some sense, the last step of this, let's put, road, okay, of these important works, okay? So I should really make this remark, okay? So what we show here? We show, and this is a little bit different from Boskayev, is that we show that if you fix the mass of a star, let's put, of course, a very massive star, okay? And if we increase the temperature, okay? So only when the temperature, see here, this line is 10 to 7 Kelvin, okay? So when you go from 1 to 10 to 7 Kelvin to, let's put 5 to 10 to 7 Kelvin, you see really an increase in the radius, even for the very massive ones. Okay, and this exists because you have the thermal pressure from the nucleons. Okay, now the temperature is, if you do the pressure rho kT, the temperature and the density we generate a pressure that is really makes in the star surface increase the radius. So that is something that you should have in account. So for very massive white dwarfs, the central temperatures need to be around 10 to 7 Kelvin to see really this increase of the radius. So what we did, so here we did this is our observational data. This is mass over radius for different temperatures. Of course, this is very high temperature, 10 to 8, but you see that here in these very massive ones, okay, you see that some of them, essentially this one that has large G, this is log of
Manuel,
G.
we see only your first slide.
Oh, excuse me?
We see only your first slide.
Only my first slide?
Only the first one.
Oh.
Yes, your slides are not moving.
So what's going on? Oh, sorry, I didn't know that. Yeah, only my first slide?
Yes, the first page. We see the first
So
page.
let me go
See
to...
the first page.
Yeah, only the first page. I see, I was doing... Oh, only the first page. And now, you see this one or no?
Yes.
Yeah, and now you see the others or no?
Yes.
Sorry. So, okay. So I was showing this increase of the radius. Are you seeing now the slide or no? Yeah? The mass and the radius or no? Yeah?
Yes, we see.
Okay. So you see this increase of the radius when you are the temperatures around 10 to 7 Kelvin, okay? These are mass over the radius and this mass over the G. So G above 10 to 9 are these stars that you are studying, okay? And are this curve that we fit, you propose a fit, an expression for the experimentalist to calculate, okay? And so what we did, we use the observations that are effective temperature, that is essentially the temperature at the surface, and the G or log of G, and from there we extract the central temperature, the mass, and the radius of the star, okay? And see if this relation, effective temperature over G, really obeys this constant that was deduced some time ago with this alpha around 2.5. So you can, after you have the TC, you can really check this relation. So this is what we did. I don't know if you can see the numbers, but these are the results obtained by Venus, okay, using Sloan SDSS, Sloan Digital Sky Survey. So you see very large, effective temperatures around 10 to 4, okay, log G above 9, okay, and here are the masses he has obtained. So you see that they change from 1.37, they have even this 1.41 that is very massive, that almost collapsed, okay, by Chandrasekhar limit, okay? But when you go now and do this study using GR, where the radius decreases, okay, so you have really a small radius here, you see, comparing to this one, okay, you see that the mass of all these stars are very close together, 1.33, 1.32, 1.30, so this, even this 1.41, in some sense, does not exist with that mass. And of course, here are the central temperatures. So you see that you have temperatures around 10 to 7 for these very massive white dwarfs, okay? So that is the message I have here, that we believe that these very massive white dwarfs that were founded, they are hot, okay? They have temperatures around 10 to 7, okay, inside them, and of course at surface 10 to 4. In our calculation, you have used an envelope where you have isothermal in the core, the temperature, but when you go to the degenerate phase, you have a temperature that goes down with the density, okay? And so that is what we obtain. And so here are the difference of, these are the points of Venus, these are our points. So what you see is that since the radius decrease, okay, the mass also decrease. So these are our numbers, and these were the numbers previously obtained by Venus that did these calculations without general relativity, okay? And so I think that's it. We found this expression for the mass. So an observer, if he gets log of G, we can get the mass, okay, depending in this, in the effective temperature they found, okay? So it's a way, of course, only valid for high G, G above 10 to 9. Okay, not for all the stars, so only for the very massive ones. And we studied stability also and found that the stability changing with the temperature, it is the first time that the radial oscillations were done with temperature for white dwarfs, okay? And we found that, in fact, when you increase the temperature, the higher frequency of fundamental mode decreases. So essentially, very hot, if you become very, very hot, the star
Manuel, please.
Becomes unstable.
You are out of
So
time.
I finish, okay? So these are my conclusions. So we found that stars near maximum mass are affected by this nuclear pressure. We really found this important result that the mass seems to be much smaller of these, all of these very massive ones, and they are hot. Okay, and this is important when you try now to understand these recent, fast and isolated white dwarfs, that they are all them very massive, okay, and also magnetic. So that's it. Thank you for your attention.
Thank you, Manuel.
Sorry for this, that we are not seeing the slide, sorry.
Okay, but will be compensated. Thank you very much.
Okay.
So let's try with Professor Cesar. Hope his internet connection is.
So I will stop sharing.
Okay,
No,
now.
yeah.
Professor
You know?
Cesar.
I need to stop sharing. I think.
Hello,
Completely imaginary. This is the first
Okay.
time that
I'm back.
So I will. Oi, César, vou parar aqui.
Cesar, okay. Okay, fine.
Okay, good to see you. Good to see you all, especially Remo. Fantastic. We are back to the internet because the cyclone, it sounds, is over. So I should share my screen, right?
Yes, you should share your screen.
Okay, so I'm doing that. Hope it works. It sounds to be.
Yes, it's excellent.
Okay.
Okay.
Can you see the screen?
Yes, I see the screen and we hear you.
Okay, good. So let me see if I, okay, can you see it better?
Yes.
Okay.
Fine, yes.
Can you also hear me because the internet is a bit unstable?
Yes, you are already stable now.
Okay, so I can start.
Okay.
So I would like to talk about the branch-cut cosmologies and about evidence, some evidences, and of course, open questions. And my collaborators are José de Freitas Pacheco. He works on the Observatoire de la Côte d'Azur in Nice, former collaborator and friend of Remo, and also Peter Hess from FIES, Germany, and also NAM in Mexico, and also Dmitry Hadishimchev. He's a good friend and collaborator here in Brazil, and also belongs to our local intranet staff, and also Benno Bodeman, our student. And of course, this presentation is in honor di Remo Ruffini. Grazie mille, Remo. So I would like to introduce a few words. No, okay, Remo. And I would like to introduce a few hints about the motivation to introduce the classical approach of the branch-cut cosmology, since we're also developing a quantum approach of this cosmology. So the main motivations for this approach are to overcome general relativity predictions of a primordial singularity. Of course, also try to describe the physical conditions of the cosmic contraction expansion periods of the universe in a consistent way, and provide an alternative approach to the inflationary and bouncing models. So in short, few words, the branch-cut cosmology is a combination of the multiverse proposal by Hawken and Hertog and complex analysis applied to the Friedman, Lemaitre, Robertson, and Walker metric. The main steps to develop this cosmology was the complexification of the standard metric applied to the multiverse conception. We got this way a closed set of complex field equations with multiple singularities. And we impose that these multiple singularities are confined to the same universe and combine all this imposition and steps with a Riemann sum to approximate the field equations to definite integrals, leading to a continuous sum of poles, which defines the branch-cut, an infinitely continuous sum of infinite poles arranged along a line in the complex plane with infinitesimal residues. This is the main steps. But of course, the multiverse conception is here, just a theoretical mathematical device for implementation of the proposal. We got this way differential integral equation in the complex domain, and we got solutions of this integral, and the solutions represent new complex scale factors represented by the reciprocal of the natural logarithm function, where beta t is a regularization function. We got this way, Branch-Cut conjugated Friedman's type equation, complex conjugated, of the represented in expressions 5 and 6. We got also a complex conjugated analytically continued as energy stress conservation law, other expressions and parameters as Hubble rate, rich scalar analytically continued also, and unlike general relativity, the analytically continued rich scalar curvature do not bend to infinity at the Planck scale, thus eliminating on the complex plane, the presence of essential singularities. These are characteristic plots of our solutions. In fact, this is the reciprocal of our solution, because the reciprocal describes the scaling in time of the branch-cut universe. So, in short, in the classical scenario of the branch-cut cosmology, the universe evolves continuously from the negative complex cosmological time sector prior to a primordial singularity to the positive one, circumventing continuously a branch-cut, and no primordial singularity occurs in the imaginary sector, only branch points. Time in the branch-cut approach is complex. If we apply a Vick rotation, the imaginary component may be replaced by the thermal time, temperature. The real component remains unchanged. These are characteristic plots of our solutions. We have here, to give you an idea of the plots of the solution, just 5 Riemann sheets. And here we have only 1 Riemann sheet to give you a better idea of a typical behavior of the solution. And we got, with this proposal, 2 scenarios. In the first scenario, we have a continuous contraction or expansion and systematic increase or decrease of the imaginary time or temperature, if we do, of course, a Vick implementation, in its negative or positive complex cosmological time sector. In the second scenario, the branch-cut, a branch point disappear after the realization of imaginary time by means of a Vick rotation, which is replaced here by the real and continuous thermal time the temperature. A mirrored parallel evolutionary universe adjacent to ours is nested in the structure of space-time, evolving backwards in the cosmological thermal time negative sector. We can discuss a lot of problems and issues associated to the conventional or the conventional cosmology, as singularity, horizon, flatness problems, and other problems. But I just would like to say the following, that in standard cosmology, the horizon problem is in part related to the ratio between the horizon size to the patch size, which scales in the form shown in expression 10, thus decreasing monotonically back in time. So the patch corresponding to the observable universe was never causally connected in the past, with the horizon size approaching zero faster than the patch size. So the limitations presented by conventional cosmology arise mostly from the fact that the ratio of the horizon size to the patch size shrinks when extrapolating back in time, causing non-causality, and from the existence of singularities that break down this ratio and thus make it impossible to restore causality. These two factors represent, in our view, in this preliminary study, the main roots for solving the cosmic singularity, the horizon and flatness problems of the universe. We're going on this study, but we can advance the following. We can restore causality in the Branch-Cut cosmology, because the Branch-Cut classical cosmology, I'm not talking about the quantum version yet, replaces the primordial singularity with a finally tunnel region, purely geometric in nature, which occurs in the classical version for densities well above the Planck scale, where the effects of quantum gravity are not yet crucial, allowing a smooth transition between the contraction and expansion phases of the universe. We have a critical region, more or less constant, between the past and the future of the universe evolution. So in the contraction phase, as the patch size decreases with a linear dependence on our solutions, light travels through geodesics on each Riemann sheet, circumventing continuously the Branch-Cut. And although the horizon size scales with that potence as shown in this transparency, the length of the path to be traveled by light compensates for the scaling difference between the patch and horizon size. Making a simple analogy with Remo likes analogies, making a simple analogy with a continuously spiraling parking garage, everything happens as if two cars left a certain level of the garage at the same time, so that one car is lower, follows a straight ramp, while in our imagination, of course, while the other car, faster, follows the longer circular route of the garage, and both arrive at their destination at the same time. Causality between the horizon size and the patch size may be achieved through the accumulation of Riemann branches in the transition region between the present state of the universe and the past events. We have, of course, a lot of open questions. We are starting this study, but following good approach to inflation, we assume the Branch-Cut cosmology is not a theory, but it's instead a paradigm or a class of theories. In this more general realm, as a class of theories, it does not make specific predictions, although specific Branch-Cut theories can make it, but instead, it can be tested by looking for generic features and evidence of the evolution of the universe. This is what we are doing now. There are many questions. How to drive the Branch-Cut cosmology? Branch-Cut cosmology can be driven, for instance, by a scalar complex field. Is it real? Or is just a motivation to think about any mathematical devices and possibilities, of course? But we're looking for quantum mechanics, yeah, in which complex insertions are so important. So we're trying to do the same here. And we have two great specialists in our field, José de Freitas Pacheco and Peter Hess. Peter Hess is an expert on pseudo-complex general relativity, together with former professor Walter Greiner. There is an equivalence, for instance, in our treatment with a complex inflation potential. We can look, for instance, for the Hubble expansion, which is part of a list of postulates that define the initial conditions of the universe. Is it possible, however, to explain how the Branch-Cut universe began? Inflation defines a false vacuum that explains the repulsive gravity of the primordial life of the universe. Is there any equivalent mechanism in the Branch-Cut cosmology? We need to complement the classical verse, of course, with the quantum verse. We are working on this topic, very interesting. Yeah, we are having so many fun doing these proposals, and they have many points of contact. But of course, and Remo certainly will complain, we also need numbers for both versions. We need numbers, of course. And another question, how many branches should be accumulated between the present state of the universe and the transition range prior to the Planck scale to achieve causality? We are working on that. And there is one question of one physicist, Argentinian one, that he asked me about the following question. Could black holes survive? Pacheco also asked me the same question. Could black holes survive to the transition region because of the inhomogeneities that give rise to structure in the spatial phase of the universe? Okay, thank you very much for our attention. I hope that the internet is not too much unstable. And congratulazioni, Remo, per la tua brillante carriera e per la tua vita eccezionale. Grazie, Remo, per aver condiviso molti momenti con tutti noi. Ok, Remo, grazie mille per tutti.
Grazie. Quante belle foto che hai fatto vedere.
Sì.
Grazie. Grazie molto.
Grazie, Remo.
Grazie, Professor Cesare, for your presentation and being on time. So, okay. So, do we have Jose Rodriguez?
Yes, I'm here.
Okay. The floor is to you.
Okay, so first, good afternoon to everyone, and thanks for the invitation. And I would like to thank Professor Ruffini for all the support that he and ICRANET gave to me and other Colombians in our PhD and our research. So happy birthday, auguri professore.
Grazie molte, Olge. Mi fa molto piacere vederti e sentirti. Molte grazie.
No, grazie a te, professore. Well, can you?
We see you.
Can you see?
We see you, but we don't
see my presentation.
No, we see your camera, but not the presentation.
No. Now, can you see?
Yes. Yes.
Okay. Thank you. So, well, I'm going to present you an ongoing work we are doing on soliton or generalized boson stars, a work pioneered by Professor Ruffini with a scalar boson star. So, first, we all know that general relativity is a very successful theory. But from the pure theoretical point of view, it's an effective theory of gravity. So it's perfectly justified to search for alternative theories to GR. So we are a little bit curious about what happens if we change the theory of gravity. And from the more phenomenological point of view, there are deep mysteries in cosmology and astrophysics. So what is dark matter and what is dark energy? And some authors have argued that they are manifestation of modification of gravity. So we focus here in a part of some kind of modified gravity theories that are called metric theories of gravity. And they have additional degrees of freedom of gravity. They have an additional scalar field, additional vectors, or an additional metric. See, in this work, we study additional degrees that are capturing a vector with a SU2 global symmetry. And we call this the generalized Proca theory, SU2 Proca theory. The generalized, this theory has the main components: the contraction of the Riemann tensor, the field strength, and the antisymmetric and symmetric abelian versions of the covariant derivative of the field. And I would like to emphasize that we have here a global SU2 symmetry. And for the construction of this theory, we avoid some instabilities and ghosts by imposing that the equation of maximum of order 2. So we avoid the Ostrogatsky instability, that is a kinetic instability that you have, a lower bound of the Hamiltonian. So you have, so you cannot extract energy infinitely. So you avoid this instability by imposing that the equations are of order 2. And we construct a non-degenerate, I didn't construct the group in our university constructed this Lagrangian that is shown here. So also we have the correct number of propagating degrees of freedom. And this is the Lagrangian. We have two main groups, let's say the alpha Lagrangians, and they have no minimal coupling of the vector fields to the metric. For example, in the Lagrangians from L3 to L6. And we have the Kais Lagrangians that are minimal coupled to the metric, but are generalizations of Proca field, SU2 Proca field. So first, we want to test if this theory is correct, to test and compare its predictions with GR. So what's the importance to use vector fields? So we will have a scalar, we have isotropy to analyze the cosmological implications. When we have a singular vector field, we have problems because we have a preferred direction in the universe, which is not seen in the CMB. So we need to introduce at least 3 vector fields that we call the cosmic triad, and this configuration emerges naturally in SU2 theory. That's why this theory is very important. So in the reference I show here, the group have tested the implication of this theory, and they have found that in order to have a gravitational wave propagation that is luminal, so we suppose that this constraint is correct. We don't argue about this is correct. We take only this as a constraint, and we can constrain the free parameters of the theory. And this condition of luminal speed of the gravitational waves is very stringent to modify gravity theories. For example, for the Ordensky theory that involves a scalar field, many terms of its action were ruled out. Also, in this reference, it was proven that there is an early inflation period that of type constant roll, and also late time acceleration that can explain the nature of dark energy. Now, we want to test the theory at astrophysical scale. So in the strong field regime and with compact objects. So also there is a question about the breakdown of GR at the singularity of black hole. So we wonder if we can avoid this singularity in this particular theory of gravity. So first, there are some previous work of Einstein or gravitation coupled to Jan Mills, that it's the, let's say, the original and the more simple version of this theory. And there are static and localized solutions that are asymptotically flat, and we call these solutions particle-like. These solutions are gauge boson stars, so it's like a generalization of the pioneer work of Professor Ruffini on scalar boson stars. So why we can find these equilibrium configurations in this theory? Because we have an attractive interaction that is gravity and a repulsive interaction that is Jan Mills. This is a necessary condition to find equilibrium configuration. So these are the good news of this, of the let's say Einstein-Jan Mills theory, that there are particle-like that are regular. We don't have singularities, and also they found black hole solution. But we will focus in this talk on particle-like solution, regular solutions. They exist, but there are bad news that they are unstable, so they are not physical problem. Now, next, there are some systems that is called the Einstein but ana-skyrmion, that also we have particle likes and black holes, and these solutions are stable. So are there particle-like solutions in this theory? The answer is yes, and we argue that they are stable. So we begin with the spherical, stationary and spherical symmetric space-time. And what are regular solutions? Regular solutions are solutions that are finite everywhere. They don't have infinites, so all algebraic curvature invariants are finite. The energy density and the pressure are finite. And they are asymptotically flat. So the M function that we define here in the line element tends to a constant value, and also the vector fields dilute when we reach infinity. And for the configuration of the SU2 vector fields, we use the most general configuration with the spherical symmetry that was derived by Witten. So we derive the equations of motions, and we define a effective energy momentum tensor as usual with the variational principles. And we tried individually each of the three functions of the configuration, and we found that the only one which is consistent with asymptotic flatness is the Topf-Polyakov monopole. See, yes, and we are planning in the future to try combined configurations like the Dion configuration, and we normalize all the variables by the gauge coupling, and we found analytic solutions for the cases of Chi1 and Chi2, and these solutions consist of a Schwarzschild black hole that is a kind of trivial, and two Reiner-Nordstrom black holes. Well, these are not regular solutions, but are analytical. And the importance is that some solutions that we have found tend asymptotically to these solutions. And the new feature is that originally in the Einstein-Jan Mills equations, there are also the Schwarzschild black hole and the Reiner-Nordstrom black hole, but they only have one charge that is equal to 1 in the units we have, in the normalized units. And in this case, we have two solutions with different charge, and in some cases, the charge can be imaginary. So we have regions where the effective energy density is negative. So this is a new feature of the theory. So in order to study the system, we performed an asymptotic expansion near the origin as a power series, and we demanded that the curvature invariant are finite. So this constrained some coefficients of the expansion, and also we demanded that the pressure and energy density are finite. So we have solutions that are regular, and the solutions And the solution of the field equations near the origin are shown in the slide. So we have that but very near the origin, the main contributions come from GR. But as we move away from the origin, we see contributions from the generalized Proca theory terms. So new features and new behavior we'll find in an intermediate region between the origin and infinite. Also, we study the behavior at infinity. It's very important here to emphasize that the SU2 global symmetry, breaks the symmetry of reflection of the vector field. So we have new solutions. And a new solutions that is a globally charged one that was absent in the original Einstein-Yang-Mills equation. So these are the solutions. Well, they are a little complicated. Also, I didn't mention, but I didn't put the field equation. They are rather complicated. You have seen the Lagrangians. They are rather complicated. So we will focus only on, I will try to focus on physics. And this is a parenthesis. I would like to thank Ruffini and Professor Ruffini and Jorge and Icanet, because when I did my PhD there, I learned one thing I learned was that try to focus first on physics and less on mathematics. It's very difficult, but you need to try it. So also we found a new solution that it's an expansion of inverse powers of R, but the exponent is not integer. So this is a new kind of solutions that were absent in the original theory. And the exponent depends on the free parameters of the theory.
Good,
And then, yes, Professor. Well, next we numerical solve these equations. It's a boundary problem that it's regular at the origin and it's asymptotically flat at infinity. So these are the solutions and these are the comparison. And we see that there are regions where the square of the charge is negative. So we have an imaginary charge. And we have the comparison. We can classify the solution by the number of times the vector field crosses becomes 0. So 1 node or 2 nodes. These are the comparisons. So we have a new kind of solutions. So these are generalization of the solutions. And next we constructed an equilibrium sequence. The parameters of the theory were taken as a control parameter, and we can see here bifurcation points. So from catastrophe theory, we can argue that at these points, the stability of some radial modes changes. So these points hints toward, yes?
Please, could you conclude? You are out of time.
Okay, listo. So, okay, right. So these are the results. So we have found particlelike solutions, and we found the equilibrium configurations and equilibrium sequences, and found bifurcation points that hints toward the existence of stable solutions that are very important because originally they were unstable and they are not physical. Okay, thank you. Auguri, professor.
Molte grazie.
Thank you very much. And is Dr. Aimuratov with us?
Oh, yes.
Thank you very much. And
one of my best students.
Hello, do you see me?
Okay.
Here you are.
Hello.
Good.
I want to pass a word first to Professor Medel. He wants to congratulate you with your birthday. So, Professor Medel.
Good afternoon, Professor Remo Ruffini. Do you hear me?
Yes, very well.
My great congratulations to your 80th anniversary. And first of all, I wish to read a special letter of President of Kazakh Physical Society, Tolegan Kojamkulov. Original of this letter I will send by Yerlan and my PhD student who will spend his long-term visit to Ukraine soon. So, dear Professor Ruffini, on behalf of members of Kazakh Physical Society and personally myself, let me express our sincere congratulations on your 80th birthday. Your work and the elegant formalism, among which is an epochal article introduction to the black hole with John Archibald Wheeler, have added beauty to the science and have been a source of deep inspiration for many scientists, including us. We cannot underline enough how crucial it is for science, especially in Kazakhstan, to keep following the works driven by sheer curiosity, which your achievement illustrates perfectly. Your visits to Kazakhstan made it possible to establish strong ties between Ukraine and several Kazakhstan universities and research institutes, which we keep developing intensively. We wish you a happy birthday and a fruitful continuation of scientific activities. With deep respect, President of the Kazakh Physical Society, Professor Tolegan Kojamkov. He very sorry because with problem with health, he cannot join us, but we hope that in next annual Kazakh Physical Society meeting, which we were planning to held in Semipalatinsk test area. This test now I'm in business visit in Semipalatinsk test site now because here some activity, joint activity of National Nuclear Center and Kazakh Physical Society. Also, we now plan to organize next meeting in next year, and Professor Kozhakov invite you to visit Semipalatinsk test area because of it's a very significant point of Kazakhstan, and we can say that it's a very dramatic and historical place. So in any case, I think that it will be very interesting to visit our meeting because of after pandemic, we wish to intensify and accelerate our collaboration, and we wish to enlarge our collaboration with Ukraine because of our government says that financing of our science will be increased more than 2 or 3 times. So it gives us large possibilities here for enlarging our operation. Thank you very much.
Very good. Say hello to Kurakov for me. Thank you very much.
So we are waiting you next year in our
definitely
Physical Societies meeting here.
Thank you. But we need to inaugurate the seat in 2 rooms in the academy are for ICRANET.
Yeah, there was some delay because of pandemic situation. So there was some delay also in activity of Kazakh Physical Society and Academy of Science. And I hope that we will start from this summer, yeah.
Yes.
Yeah, our joint work.
Okay.
Thank you very much for your attention.
Okay, let me continue. Do you hear me? Do you see my slide? Let me share.
No, not yet your slide, but
okay, now?
Yes. Yes.
Okay. Thank you for inviting me to give a talk on this beautiful occasion of happy 80th birthday of Professor Remo Ruffini. And today I will present my talk based on kind of, let's say, fantasy of mine, saying that the redshift estimates of short Cherubis can be made on the i-Peccei-Quinn correlation. And probably all of you know what the gamma ray bursts are, but 5 minutes GRB crash course.
Please.
Sorry?
No, excuse me.
Okay. I will make a 5 minutes fast GRB crash course to those who doesn't know what the GRBs are. Only the facts. The first observational fact, they have isotropic distribution on the sky. That means that they are extragalactic origin, and that means that they have a high Z, high redshift. This fact took almost 30 years to prove, and nowadays it looks like this. If you look at the sky, the whole sky, no matter which point you are looking at, is covered by the GRB. Once occurred, never repeated. And to the time, for example, the Fermi-GBM observed more than 3,000 GRBs over the 10 years more. And the same situation is for the other GRB missions started from the earliest to the current operating missions. The second observational fact you should know is the temporal B-modality, the so-called long and short, which was discussed many times. And each GRB mission since Konos in the early 1980s, every GRB mission reproves this phenomenon. What we understood now on this temporal B-modality, this phenomenology, this hints to the progenitors, and nowadays we came to the point, the community came to the point that the progenitors for the long GRBs is a collapse of some massive stars, binaries, single, and for the long GRBs and for the
You lost.
Yerlan, can you hear us?
Yerlan? You see us in the screen. It's okay? Ours?
No, it is.
Ours is broken?
I see you.
Okay.
It's problem.
It's not on our side. It's on their side.
Okay.
Yerlan.
Yerlan, we lost you. Let's wait for some moments.
In the meantime, let me leave you with one of the best Israeli ones.
Let's wait 2 or 3 minutes, please.
You're doing fantastic.
Yerlan, we lost you for some minutes.
Okay, okay. Do you hear me now?
Okay, it's okay. Please go on.
Yes, let me share again my screen. Okay, at which point you lost me? Okay, probably this, the second observational fact. Okay, I hope you hear me. Okay, the second observational fact is that the temporal beam modality, as I had said, and it comes with two flavors, GRBs being emitted in less than 2 seconds and more than 2 seconds in the main gamma ray range. The third observational fact you should know is that GRBs emit on the entire electromagnetic spectrum, and they're present from TeV, the very high energy, to the radio, through all these optical and UV and X-ray bands, which means that there are very energetic processes happening, and the site where it happens is very complex morphology, and it puzzles many scientists to give a very simple and very clear picture what is happening and what is the radiation mechanisms. Of course, I don't mention the non-electromagnetic counterparts as gravitational waves and neutrino, which should be mentioned separately, of course. But today I want to focus, based on these three simple observational facts, I want to focus on the phenomenology. The most famous one culminated through the years by the several groups, and it culminated in the so-called i-Eiso correlation by Professor Amati. You should see his talk of this morning session. What it means, at the first, when it was published, it consists of 12 long GRBs, and it says that there is like a correlation line behavior between the peak energy of the spectrum of the gamma radiation and the isotropic energy calculated based on the redshift observed. So these 12 GRBs are observed by Beposack's mission, the epochal mission as well. And based on these 12 long GRBs with redshifts, it was possible to measure, to build this correlation. And it was 2002, and time passes, and in 2019, almost 200 long GRBs with redshifts again are still following the same correlation. Slightly changed the normalization of the index of the slope, but still it holds this phenomenology. Okay, and this is for the long GRBs. But you can ask, what about short GRBs? And as Professor Amati said this morning, there is another sort of correlation that exists, and it needed longer time to collect the statistic, but it should exist as well. And it's called Zhang relation. It's the same Peccei-Quinn correlation, but as it was shown, as you can see now as well, it was built up on base of 7 short GRBs with redshifts. It's red squares here. And by the way, the lower part is the long GRBs, the higher part is the short GRBs, since they have higher peak energy of the spectrum. Okay, it seems that it follows the same, more or less the same correlation, with the slope slightly different, with index harder. And as time passes from 2012 to 2018, more than 31 short GRBs are already included in the sample, all of them with measured redshifts, and still holding the same correlation. And you can see here 817 is almost on the border of 3 sigma limit. And it's very unusual, as it was said already many times on this conference. And as well, here is 090510, the only GRB, the short GRB with measured redshift and the GV emission present to the moment. All of them are ordinary short GRB with measured redshifts, and you can see the correlation still holds. Then you can ask, so what is the problem? Both Amati and Zhang correlations pretty good describes the GRB energetic correlations. but I can say that they both highly rely on GRB with measured redshifts. And actually the whole GRB physics relies on the redshifts to calculate isotropic energy, then put it to the whatever modeling you want to do. And having the Z gives you a possibility to shift to the rest frame to study the physics properly. And here I want to say that Professor Ruffini always says and always asks, please calculate this in the rest frame. So that's why he wants to see the proper time and the proper physics on the side. And it's very crucial to have a Z measure. But what we can say on statistics, for example, the Fermi-GBM catalogue, to the moment of 2020, it observed almost 3,000 GRBs, and among them only 181 GRBs have measured redshifts. So if you compare long to short, it's 10 times less short GRBs observed with redshifts. And it means, for me at least, it means that 90% of GRBs, 90 I'm saying because you can include other missions like Swift, BPOSAX, Peccei with measured redshifts, and you can increase this number only to 10 to 15%, and it means that 90% of data you should practically throw and you cannot use because you simply don't have a redshift. And for me, it was ridiculous. And to make a proper rest frame physics, you only need a redshift. So there is a simple ansatz. Let's suppose that there are really two long and short flavors of GRBs, and the Amati and Young relations are true. Then you can simply vary Z parameter within a certain observed range, the real observed range of real GRBs with redshifts. And by simply varying this and calculating the E peak of the rest frame and i-Eiso, you can build a line for every GRB parameter and see if it matches and it crosses, intersects the EPK-ISO correlation, and it's 3 or 1 sigma areas. So this was my ansatz, and to do that, we first need to focus on short GRBs properly and to measure and to collect the sample with proper measured peak energy. Because, for example, again, for the Swift, due to its limited sensitivity, the energy range, it cannot detect the hard peak over 150 keV, which is actually the one for the short, so they have harder spectrum. So together with another student, a former student of Remo Ruffini, Marco Muccina, we did this sampling, and he collected accurately EPIC measured short GRBs and reconstructed this Zhang correlation with the slope of 1686 and the index 0.49. And by the way, here the red points are those GRBs proposed. Also, there is like a fire shell model proposing the estimate of the redshift, and it lies within the 3 sigma limit, which is quite good. So we can as well use it, but here we just use the black circles and the red ones are just to show that there is like a good ideas also happening there. So we have the slope, our own slope, based on the accurately collected sample of short GRBs with measured redshifts. Then we need the Fermi Catalogue data. So the reasoning is very simple. So Fermi captures securely the peak energy of the spectrum, and it operates. It's more than 10 years and has a lot of GRBs measured, like over 3,000. And it also provides automatic fitting of 4 models in hand, to the most popular ones, to fit the spectrum, and it calculates also with the chi-square. It calculates the best fitting model to this kind of spectrum of every GRB, and it puts in the catalog of the parameters as well. Okay.
Yeah, can you accelerate, please?
Yes. I'm almost done. So we did a very simple sampling. We just selected short GRBs, less than 2 seconds, and we choose the CPL, so it's computerized band models as best fitting models. So we result in 223 short GRBs in hand. We can do the following. We vary the Z from the closest distance observed GRB Z to the farthest, like 9.2, the famous one. And we see, and you can see that every point here is the pre-calculated parameters, which matches on the plane of i-Eiso correlation. You can see that here, due to the log scale, it goes tighter and tighter. But all of these 223 GRBs should follow more or less the similar path, crossing 3 sigma only, or with 1 sigma still, and to the line itself, or crossing all the lines, since it has the lower e-peak, and it's possible when varying Z to the highest points, like here is like Z is equal 10 in every one of this. We vary Z and we have this crossing, where the crossing is simply intersection. It's like you can calculate it analytically. It's like line-line intersection, simple analytical solution. So for every 223, we did the same, and we match. We use also the robust algorithm, the Bentley-Ottoman algorithm, to calculate the intersections of each point and listing them. So what we have as a result, we have a long list in this table, and we see that some of GRBs, as it was shown, cross like only 3 sigma, or goes to the 1 sigma, or to the line itself. And you can see we collected all these redshifts result as an inverse problem. So giving that the cross this line, we have i-Eiso in hand, and we back calculate the Z, and this Z are present in this table. And doing a little preliminary statistic, we can see that when it crosses the line at 128 GRBs going to the line, not turning back, we can see that median and mean values are more or less similar and coincident. 0.8, which is actually the good estimate for the short GRBs. And for example, if we refer to the Berger 2014, it gives 0.5 to 0.8 estimate of the median redshift of the short GRB with measured redshifts. So we are still progressing on this. And as a summary, I can say that we propose this simple method to estimate the redshift, which is quite needed. And it's a direct usage of the i-Eiso correlation, apart the cosmology, of course. There is a circularity problem which can be resolved as well, which should be taken into account. There is instrumental bias could be involved due to the Fermi usage only. So we need further to test this set of synthetic Z we obtain with other correlations. So we just take this Z and pre-calculate this i-Eiso or L-peak, e-peak as ion correlation, and put it on the plane and check if it holds still. And we need to merge also other missions, Catalogue, like Swift, as I said, Peppos, and so on. We didn't show here the special case of 17 or 817 and probably 090510. We didn't calculate that on our algorithms. But we need to pay attention on this because they are very special. And as well, we are currently applying this method since it works for the short GRBs. We need to apply it for the long GRBs, which much larger sampling, like 200, and the number goes over 2,000 without measured redshift. So we want to apply this, and the results will come short after. So stay tuned. And as a last slide, I show and want to emphasize the one of the manifold characteristics of Professor Remo Ruffini. It's a hospitality. And this picture you can see, he invites us. Here you see the Jorge Rueda, which is present in Nice, and other students with Professor Remo Ruffini. He invites us. It was the beginning of 2018. He invites us to have dinner in his apartment to discuss some physics in a very friendly atmosphere. And it was very good time spent in Pescara together with new students, multicultural multicultural team, and of course, seeing and discussing the physics like 24 hours. Professor Ruffini is ready to discuss the physics, and it's like in his nature as well. So, and it's thanks to his hospitality. He's a very kind and open person, and I want to congratulate you, Professor Ruffini, with your 80th birthday. Happy birthday. Thank you.
Thank you very much, Yerlan, for your nice words. And I have to move to the next speaker. We are 20 minutes delayed. So okay. Professor Quevedo, hope he is with us.
Yes, I am here.
Welcome, Professor Quevedo.
Okay, let me try to share my screen. So can you see my screen?
We see your screen, we hear you. It's okay.
Okay, very good. Good morning, everyone. I first would like to say that I'm very honored to participate at this conference, and I would like to thank Remo Ruffini for his constant support, and especially for always being some sort of inspiration. I think that his deep knowledge of physics is really what is the important part of his activity as a scientist. This is why I personally believe, and I believe most of us believe, that Remo Ruffini is an inspiration for all of us, and I would like to dedicate this talk to his anniversary. And in some sense, the results of these talks are related to some talks we had many years ago, about 10, 12 years ago, when I was visiting Pescara for 1 year. So let me start with the talk, with the ideas of the talk. First, I would like to talk about the motivation of this talk. Then I will talk about curvature eigenvalues, and then I will propose a new method for matching solutions, different solutions of Einstein's equation. Then I will go to show some examples in the case of black holes in Einstein theory and spherically symmetric gravitational fields. So let me try to go to the next slide. I don't know why I cannot do that. Just a minute. Okay. Okay, very good. So the motivation is very simple. This is a very old problem, which has to be with classical general relativity, in the sense that, according to the theory, in order to describe a gravitational field, especially in the case of relativistic compact objects, we need to have at least two solutions, two exact solutions of Einstein's equation. And in some sense, especially in the case of relativistic compact objects, we have to match both solutions at the matching surfaces, which is usually the surface of the body. So the question is, how can we match two different solutions of Einstein's equations, especially an interior solution and an exterior solution? So this problem is very important from the conceptual point of view, because general relativity is supposed to be a theory of gravity, and so it has to be in the capability of describing relativistic compact objects. Then, for the description, for the physical description of these gravitational fields, we expect that we will find some particular conditions for matching two different solutions. So in fact, we are not supposed to match any solutions, but only some particular solutions which have especially some physical significance. So let me just remind you what we usually do in order to match two different solutions. And in general relativity, we start from a surface, which is the matching surface. We have from one side, this V plus represents one exact solution of Einstein's equation. V minus represents an exact solution of Einstein's equation. And we have to match these two solutions along this matching surface. So we know that in order to do that, we have to introduce two concepts. One is the concept of induced metric, which is this Hij I have here, which is the metric along this surface. And then we have also to introduce the concept of extrinsic curvature, which is given in terms of the covariant derivative of the normal vector to this matching surface. So these two objects, which are usually called the first fundamental form, which is the metric, the induced metric, and the second fundamental form, which is the extrinsic curvature, they have to satisfy some conditions. These conditions were proposed by Manuel, Lichnowsky, and so on almost 100 years ago. And they have been, so to say, described and represented in different ways. But the final, the interesting point in this case is we have to satisfy two conditions. The first one says that the induced metric, which is induced from the exterior part of the solution, and the induced metric from the interior part of the solution, they have to be exactly the same along the matching surface, and also the extrinsic curvature. So that means that the usual matching conditions say that we were not supposed to have discontinuities along the matching surface, discontinuities for the metric, induced metric, and discontinuities for the extrinsic curvature. They have to be continuous quantities in order for the matching conditions to be satisfied. So one of the questions which is open in all these procedures, which are called the C2 procedures, is that the matching surface is completely arbitrary. We can put it anywhere, and usually we don't know where to match the two solutions, especially when we don't have a surface which is the limit between the interior solution and the exterior solution. So this is an open problem in these C2 matching conditions. And it's called C2 because it includes the second derivatives of the metric, which are here in the extrinsic curvature. This is what they are called the C2 matching conditions. So what I am going to propose is a different procedure to match solutions, because in particular, it is very important in order to explicitly apply this method to have special solutions. They are called specially adapted coordinates. These coordinates I am denoting here as yi. This is just the theory. This is a mathematical definition. But when we want to apply this to the particular problem, it is very, very difficult to find the corresponding coordinates, because these quantities, the extrinsic curvature and the induced metric, they depend on the coordinates you are using. So this is why it is very important to choose the appropriate coordinates, and this is an open problem in this matching procedure. So I am going to propose a different procedure in which it is not necessary to have any coordinates. The procedure doesn't depend on coordinates, and the procedure gives also different results, different from the ones we get in the C2 matching procedure. So let me just start with the definition, and then I will show exactly how to make the calculation. So the definition of the C3 matching conditions is the following. Imagine you have the curvature eigenvalues of the Riemann curvature tensor. So I will show you that there are 6 different, in general, there are 6 different eigenvalues for the curvature tensor. So we start from them, and we also calculate the derivatives of these eigenvalues with respect with some spatial coordinate. In this case, I'm calling it R. So we find all the extrema of these eigenvalues, and from all of them, we choose one particular, which is the maximum of all these radius, in those spatial distances in which the first derivative of the eigenvalues is equal to 0. That means we have some extrema at these points. I take the greatest of all these distances, and I call the repulsion radius for some particular reason I'm going to explain right now. So the point is that now, because I am using also the derivative of the curvature eigenvalues, I will have to introduce here, I will have to analyze the behavior of the third order derivatives of the metric, and this is, we call it C3 matching conditions, because we are dealing with third order derivatives of the metric. So the point is that now with this new procedure, we can also determine the position of the matching surface. The position will be given, in this case, for any radius, which is within the range within the repulsive radius and infinity. You can take any one of them in order to apply the matching conditions. That means the position of the matching surface is not arbitrary, but has to satisfy this condition. I will explain why. And then the matching conditions themselves, they say the following, that the eigenvalues from the exterior part of the solution, from the exterior solution, they should be exactly the same at the surface matching as the eigenvalues of the interior solution. So we have continuous values for the eigenvalues of the curvature tensor. This is the idea, okay? So I will try to explain what is the idea, the physical idea behind these conditions. So let me just explain to you how to calculate the eigenvalues of the curvature tensor. There are many ways to do that. I will use the one which is, I would say, one of the easiest one, in the sense that you can put it with your computer and you can do all the calculations. So let's start with the metric, the standard form of the metric, and I introduce a local tetrad, which is actually the tetrad, a simple free field observer will use in order to investigate these gravitational fields. And we know that when we use tetrads, then we can use the Cartan formalism in order to find the corresponding connection form and the corresponding curvature form in this way, so that at the end you have all the components of the curvature tensor, which are given here, all the components in terms of these local tetrads. So the point now is that you can take all the 20 independent components of the curvature tensor and put them into a particular matrix, which is a 6x6 matrix, which is done by using this representation. That means for each pair of indices which are related to the components of the curvature tensor, then you introduce a new index, which are called bivector indices. And then in this way, you represent all the components of the curvature tensor in a 6x6 matrix. And this is the main idea. So for instance, if you look at the Bianchi identity, the algebraic Bianchi identity, which means that you have a relationship within the components of the curvature tensor, in this bivector representation, it is written in this way. So that means that this implies a condition, a symmetry condition, a symmetry property for this Riemann matrix, this 6x6 matrix. So in general, one can show the following. If you take this general form of the metric of the matrix for the curvature tensor, and you apply, in this case, the Einstein's equations in these local tetrads, then what you obtain is that the general form of the curvature tensor is given in terms of these matrices M1, M2, and L. L is given in this way, M1 is given in this way, and M2 is given in this way. Here, I am representing the general form of the curvature tensor for a perfect fluid solution. You can do it for any tensor, energy momentum tensor you want. You will always obtain some very particular representation of the curvature tensor. So this is the Riemann curvature tensor in bivector representation. This is a 6x6 matrix. And the idea is that once you calculate the explicit form, the explicit components of this curvature tensor, then you go ahead and just calculate the eigenvalues of this matrix. And since you have a 6 times 6 matrix, you can obtain at most 6 different eigenvalues. And this is the idea. These eigenvalues are now independent of the coordinates because they are actually scalars. These eigenvalues were used many years ago in a different representation by Petrov, and this is why today we know as the classification of gravitational fields in terms of the curvature tensor by using the Petrov classification. So, and in the Petrov classification, when you use these eigenvalues, of course, all the classification, all the types you obtain for all possible gravitational fields, you always obtain something which is independent of the coordinates. And this is one of the main ideas of this procedure, in which you don't need any particular coordinates, you use just scalar quantities and they don't depend on the choice of coordinates. So once you have this, then you can try to understand the behavior of these eigenvalues. So the standard behavior you obtain when you calculate the values of these eigenvalues, then there are only 2 possibilities. One is when you plot the eigenvalue in terms of some radial coordinate or some spatial coordinate, for instance. There are only 2 possibilities. The eigen goes to infinity, the infinity goes to 0 if you have an asymptotically flat solution of Einstein's equation. It's asymptotically flat space-time. So when it goes to 0, if you have a singularity, then the eigenvalue will go to infinity as we expect. This is the standard behavior, for instance, in the case of the Schwarzschild metric. But you have also other metrics, for instance, the Kerr metric and so on, in which if you look at the behavior, it's completely different. When the eigenvalue goes to infinity, the radial coordinate goes to infinity, and you see that the eigenvalue goes to 0 because it's asymptotically flat. But once you go to 0, the behavior can change, and from being positive, for instance, it goes to a region in which it is negative. The interpretation we are giving to this behavior of the eigenvalues is that there is a particular region in which something which effectively can be interpreted as repulsive gravity, then in this region, you will obtain effects that could be effectively treated as repulsive gravity. So then at this point, which is a maximum of the eigenvalue, we define the repulsive radius, which is the maximum in this case, which is closest to the value of r equal to 0, closest to the singularity, as we know usually happens. So then, if we want to match an interior solution, the interior solution should avoid all these repulsive effects because we don't see them in nature. Repulsive gravity is nothing we can detect in nature. However, in order to avoid this repulsive gravity, we put in this part, inside the repulsion radius, we put a different solution, and this is the interior solution. That means we cover all this part of space-time in which repulsive gravity is effectively seen. We cover it, but in interior solution. This is the main idea. So then the matching radius will be anywhere between this point, we have the repulsive radius, up to infinity. In any point, for instance, here you can put the interior solution here, anywhere in this point. So this is why what we need the first derivative or the eigenvalues with respect to this radial coordinate. So this is the definition of repulsive values. Let's see if this idea corresponds with what we see in some particular solutions of Einstein's equation. Let's do that for black holes. So just making all these calculations calculating all the eigenvalues of the Kerr-Newman black hole, one can show that the repulsion radius of the Kerr-Newman black hole is given in this way in terms of the mass of the black hole, the charge, and the angular momentum, or the specific angular momentum, which is given here. So that means in this case we can solve all these conditions analytically, and in particular for the case of the Kerr metric, we see that the repulsion radius is given in this way in terms of A, which is the Kerr parameter for the Kerr black hole. This is J over M, the specific angular momentum. In the case of the Reis-Nostrum black hole, the repulsion radius is given in terms of the mass and the mass and the charge of the body. And in the case of the Schwarzschild radius, we have no repulsion. The Schwarzschild black hole, we have no repulsion radius. So schematically, one can show the following situation. Here, the green curve denotes the ergosphere of the Kerr-Newman black hole. The red curve is the horizon, and the blue curve denotes the repulsion radius. So we can see, for example, that in the case of the Reis-Nostrum black hole, which is this one, this circle here, it is inside the horizon. So that means that there is no problem with repulsion inside the horizon, because we can never see this part of the space-time. Then in the case of the Kerr-Newman black holes, there is a part which is outside the horizon, outside this red curve, and also outside the ergosphere. So in principle, we should be able to detect this repulsion in the case of the Kerr and in the case of the Kerr-Newman black hole. And in fact, if you look at the geodesics of these black holes, you will see that especially in these regions, you see effects that could be effectively interpreted as repulsive gravity. So that means that our definition, our intuitive definition of repulsion, is in agreement with what we know from black holes. So let me now apply this to a very specific gravitational field, which is the case of spherically symmetric gravitational fields. We know that for the exterior spacetimes, we have only one solution, which is the exterior Schwarzschild solution, which is given here. Then let me just apply first the C2 matching conditions, which means I have to calculate the induced metric and I have to calculate the extrinsic curvature. So the explicit expressions are given here in terms of the mass of the body, and also here in terms of the mass of the body for the extrinsic curvature. So the point is now, let's take, this is for the exterior part of the space-time. Let's take now a solution for the interior part of the body, which is a sphere. Let's take, for example, the Tolman-3 interior solution, which is what we usually know as the interior Schwarzschild solution. It can be written in this way. This is a solution which is represented by the perfect fluid in which the density is given in terms of these two constants. M is somehow the mass of the body. K is a constant which we interpret as the radius of the surface. The pressure is given in these terms, and so this function is just given in this way. So this is an exact solution of the Einstein's equation for a perfect fluid, and the point is, can we match this interior solution with the exterior Schwarzschild solution? So, and we will see how to do that in two cases. First, in the case of the C2 matching conditions, and then in the case of the C3 matching condition. So then let's calculate the induced metric from the interior part of the spacetime. Is given in this form. Let's calculate the extrinsic curvature from the interior part of the spacetime, and then let's see if we can match all these expressions, the interior curvature, the interior extrinsic curvature with the exterior one. They have to be exactly the same on the surface, and also the induced metric has to be exactly the same on both sides of the surface. So it is easy to see that if you put the surface at the value r equal to k, which is a constant, then both conditions are satisfied. The induced metric has no discontinuities across the matching surface, and the extrinsic curvature has no discontinuities across the matching surface. That means that according to the C2 matching conditions, we can match without problem the interior Schwarzschild solution with the exterior one. Let's now do exactly the same with the C3 matching conditions. Then we have to calculate the exterior curvature eigenvalues, which are given here for the Schwarzschild metric, and for the interior Schwarzschild metric, they are given here. You can see that there are 6 different eigenvalues for the interior part, 6 different eigenvalues for the exterior part, and then you obtain here an algebraic system of 6 equations, and the question is whether you can satisfy all of them at the same time on the matching radius. So one can show that in general this is impossible. So that means according to the C3 procedure, it is not possible to match the interior Schwarzschild solution with the exterior one. So then we have 2 procedures with 2 different results. What is the best one? So our interpretation is the following. So we obtain different results because we know, look exactly at the form of the metric. The C3 matching conditions imply that rho should be 0. That means the density of the body should be 0 at the matching surfaces, and also the pressure should be 0 at the matching surfaces. We apply these conditions, the C2 condition, to a solution which has constant density. That means on the surface, it can never be 0. So this is the reason why C3 says they cannot be matched. They can be matched only when the density and the pressure are 0 on the surface. And from our point of view, it is better, from the physical point of view, we believe that it is intuitively better to have a solution in which the density as well as the pressure, they go to 0 at the matching radius. This is what we believe, that the conditions we are obtaining from the C3 matching is more physical. They are more physical than the conditions we get from the C2 matching. So we just did it for one particular example, which is the Tolman 3 solution. But in general, there are many, many interior solutions which in principle can be matched with the exterior solution. We did it for about 20 different solutions, and none of them can be matched with the exterior Schwarzschild solution. That means that from the point of view of the C3 matching condition, there is no interior solution, at least from the solutions which are known analytically, there is no solution, interior solution, with a perfect fluid that can be matched with the exterior Schwarzschild metric. So in general, we can show that for any spherically symmetric gravitational field, the condition from the point of view of C3 matching procedure, the condition for being able to match these 2 solutions is that the pressure and also the density, they should be 0 at the matching radius. This is something that intuitively we expect. And once you have discontinuities there, then you should apply a different method. But from the practical and from a conceptual point of view, we see that the C3 matching conditions generate physical conditions of physical restrictions on the form of the metric. So to conclude, let me say, C3 matching conditions are invariant, which is very important when you want to do something that doesn't depend on the coordinates you are choosing. This is a very important point. Also, if you compare this procedure with the C2 matching procedure, then we can determine the position of the matching surface, which is always a problem when you use C2 matching conditions. Also, as we can see, at least in the case of the spherically symmetric gravitational fields, our results are physically plausible in the sense that we obtain that density and pressure should be zero at the matching surface. And this is something you expect just from the physical point of view, something is some intuitive condition. And the following property of the C3 matching condition, and they are easy to be implemented, especially with any one of the modern computer programs in which you can very easily find the eigenvalues of any solution, and then you just go ahead and try to find the properties of the eigenvalues and see whether you can match different solutions with different eigenvalues. So the first work on this idea of matching condition was presented in a Marshall-Grossman meeting, and in fact, the first paper published on this idea was in the process of the Marshall-Grossman meeting. But then I worked with some colleagues, some students, and this is a short list of the most important papers on this idea of proposing a different and alternative method to match solutions in Einstein's equation, of solutions of Einstein's equation, especially solutions that could be applied to describe the gravitational fields of compact objects. Okay, thank you very much. And again, Remo, happy birthday, and thank you very much for being a source of inspiration for all of us. Thank you.
Hernando, it's a great, great pleasure to see you directly in this occasion. And please bring to the people in Mexico all my deep memories, and thank you and everybody for the constant friendship which has gone through so many years. And
thank
for
you very much.
A special thanks for all the opening you did all over ICRANET Center, always with very good sense and beautiful results. Thank you again, Hernando.
Thank you. Thank you.
Thank you, Professor Quevedo,
Mm-hmm.
For sharing for your clear presentation and for sharing your morning with our afternoon here in Villarati in Nice. And let's go on with Professor Marco Tavani.
Eccoci, Marco, dove siamo?
Eccoci, ciao.
Come in.
Hello everybody. I'm very happy to be here. Can you hear
Eccoti.
me?
Un minuto solo. Where do I put the Allora, prima di tutto ti ringrazio. It's okay. Prima di tutto ti ringrazio molto. Siamo legati un po' a tutto il mondo e anche qua nel nostro piccolo abbiamo Zvi Piran che è qua, Narek Sakian dell'Armenia, ma siamo in contatto, come tu ben capisci, dalla mattina alla sera, cominciando dalla Corea, poi andando avanti. È stato un grande piacere e un grande onore.
Sì.
Quindi oggi che terminiamo, è molto bello che tu sei con noi,
Sì.
anche perché stiamo non perdendo tempo, perché stiamo, guarda, è proprio con te. Look, it's incredible this coincidence. When I first had this evidence, about the many jets on a very short time scale, and was Marco who said, of course, these are the jets of the Cherubini. Te lo dobbiamo spiegare meglio. Now I'm explaining to Zvi, but we really have understood the inner machine completely of the GRB. Therefore, we need to see you, and for the moment, let me thank you that you come and show you and give the greetings.
Yes, thank you.
Ma
Thank
dobbiamo
you very much.
vederci perché abbiamo una quantità di fisica enorme e ci sono dei risultati che dobbiamo parlare perché sono eccezionali.
Thank you, Remo. Thank you. Thank you very much. It's a pleasure, of course, to be here today. I'm sorry that I cannot be in presence, but Remo has been in a sort of explosive force, so to say, in physics and astrophysics and general relativity over many, many years. Many students, many people were helped by him. And I cannot, personally, I cannot forget, at some point he helped me very much in my endeavor when I was a PhD student at Columbia University. And since then, we have been very close, of course, then Princeton, then of course, general relativity, then of course, Johnny, and so on and so forth. So I think over the years, Remo pursued this project, this wonderful project of teaching, of spreading out really a sort of sense of research, and a pure sense of research that independently of how difficult it is, the problems that you have to confront with, but the enthusiasm. And many students who actually now are professors around the world. And it's a very beautiful thing, Remo, to see your students who are really filling the space of physics and astrophysics around the world, just because of you. I think this is a wonderful message. And I hope that you will continue to do that, of course, for a long time. And I really want to wish you a very happy, of course, birthday. This is the beginning of course, a lot of work, a lot of things that you will be doing now, starting today.
You will.
And I just want to conclude my little saying, really, that I'm very happy to be here with you. Personally and scientifically, and I hope that we can collaborate in the future very strongly. Thank you, Remo.
I am here now in Nice. This is the villa of Ikranet in Nice.
Yes.
And at the first floor, are you listening? At the first floor today, the people who received the award, namely Tzvi Piran, Sunyayev, Rashid Sunyayev, and the head of Max Planck, who sent up the German-Russian telescope, signed the wall. Therefore, to get on that wall, which was signed among others by Gelman and other people, there is still a place for your signature. Therefore, put a visit in Nice, and you have to help us to finding people who understand our great mission and convince them to give us funds, because the funds which are given at the moment are incredibly unacceptable. And maybe you can hear my concluding remarks if you stay on. And we have some incredibly important result which will stop bad science, in my opinion, if people understand the message. But good science is gone. I am trying to convince the people of OHB in Germany, which have OHB in Italy, who are the one that they made the Euro satellite. They created the Gavazzi and so forth, which are part of OHB. I'm trying to convince them to make a new satellite for this topic that I'm telling Tzvi, this micro 10 minus 14 second, which characterize the prompt radiation. This is the new discovery we have done. It's enormous and will change astrophysics because it will insert all the fractal structure there is an enormous thing, and even biology and maybe life comes out of this structure. Therefore, please allow me to explain to you in a few words in the next days this thing, and keep us on in touch. Okay.
Okay. Okay. Thank you, Remo. Okay. Thank you.
We go on. We need your help. This time we need your help because people are really doing bad science and they are completely wrong. It's no problem. I will send you a letter which I sent to someone in the government, and you can think over. I will send you the letter right away.
Okay.
Okay?
Okay.
Ancora grazie.
Grazie a
Thank
tutti.
you very much. And let's go to the concluding remarks.
Okay.
Luca Izzo. Ah, Luca Izzo. Ah, yes, very good. Luca Izzo rimane. Marco, se puoi rimani. Ci sono solo 2 interventi. Luca, che è venuto a farvi una grande conferenza ieri, ce n'è da qua. Luca è fantastico perché abbiamo scoperto il significato di una nuova sorgente. E quindi se vuoi sentirlo e poi io farò le conclusioni. Ancora grazie. Ti ringrazio molto. Ciao. Ma perché il mondo è critico, non è critico per Remo Ruffini, è critico per la scienza italiana, perché c'è una delle più grandi truffe della storia. Quindi, e c'ho le prove semplici, vedrai. A presto,
Okay,
nella più grande tradizione della nostra fisica.
Grazie.
Ciao.
Ciao, ciao, ciao.
Però incontriamoci, te lo devo dire a voce. Va bene?
Ciao. Ciao, Professor Tavani and Luca now, please.
Yes, just trying to quickly share.
You have to understand.
Can you see my slides?
We help. You understand?
Can someone switch off microphone of Professor Ruffini because I really hear a lot of noise? Okay.
Grazie.
Okay, so I'll just prepare a few slides to celebrate the birthday of Professor Ruffini that actually was yesterday, not today. And in these few slides, I would like to highlight how the heritage of Ruffini has influenced my current research in GRBs and not only. So I needed to recover some very old slides about my PhD research. You know, I made my PhD starting in 2008 at La Sapienza with Professor Ruffini, studying this model of GRBs, the Fleischer model that was completely based on theory that was established by Ruffini and collaborators during last century in the 70s. Actually, you have surely heard about the formation of the Fleischer scenario in GRB, but actually when I arrived in the Ruffini's group at La Sapienza, the group was mainly based on simulating the emission of gamma ray bursts instead of directly analyzing the data that were obtained from the same satellite. Indeed, one of the main parameters that was described in the Fleischer model was the baryon loading, that was actually the parameter that described completely the evolution of the Fleischer scenario, because once one can determine the baryon load according to the value of the baryon load, one can determine directly the temperature, the laboratory radius, and other properties of the PGRB emission and the consequently emission in the afterglow of gamma ray burst. However, this operation was not easy at the epoch when I arrived because people were not analyzing data directly. So thanks to inspiration of Professor Ruffini and also other professors at ICRANET at that time, I started to work directly on the data obtained from currently and actually from satellites that were operating at the time and actually are still observing the sky, such as Swift, Fermi, and Bazzi. And my operation was mainly, sorry, I'm just receiving some notification, to start to implement in a completely theoretical group the meaning of data analysis. And I think that thanks also to the support of students and Professor Ruffini, we started to analyze the emission of gamma ray bursts, in particular the time-resolved spectra, to search for signature of the P-GRB emission, because once one could identify the P-GRB emission in principle and the thermal component underlying the P-GRB emission, one can determine all the parameters of the system. This was done for some GRBs until we started to work on the famous Indian gamma ray burst on INO 618. Indian because it was observed, was the first gamma ray burst observed by an Indian satellite that was operating in 2009. And to my memory, probably this was the only GRB that satellite detected, because I did not hear about other GRBs detected by that satellite. On INO 618, a nearby GRB at Redshift 0.5, very energetic, that was showing a peculiar behavior in the prompt emission with a prolonged precursor that I was really crashing my head with the wall in order to find any signature of the PGRB, because a more detailed analysis showed that the entire first episode lasting 50-60 seconds was characterized by the presence of a thermal component. And thanks, I remember the day that I entered in the office of Ruffini saying, Professor, I'm sorry, I could not find the PGRB, because PGRB is a rapid flash, is when the plasma reaches the optically thin condition and immediately emits a flash of thermal radiation, something like shock breakout, but it's not a shock breakout. But this precursor lasting 50-60 seconds was really anomalous. And I remember that the meeting with Ruffini triggered a new research line, because from the analysis of the Indian GRB and the 2-episode proposal with the thermal component, in particular, I developed the method of the thermal component that has been really precious in my current research. This analysis triggered the induced gravitational collapse scenario at the epoch, with some works proposing the binary origin for long gamma ray bursts associated with supernova, and the 2-episode emission that were responsible for the observed phenomenology. Now the model has improved with many cases, many different scenarios, possibility, and outcomes. Indeed, I'm not now updated on the status of the current model of Professor Ruffini, but I'm proud that I've been one of the first ones to trigger this model that is probably currently one of the main research lines of Ruffini, Ruffini's group in Pescara. However, why I meant about the heritage of Ruffini? Because the analysis of the famous thermal component was very useful in my current research, because in one of the very nearby GRB that we have observed within the Stargate collaboration, nearby 0.03 redshift, but very low luminous, we have actually implemented the same analysis that we developed for the Indian GRB on INO 618 to this event, and we found indeed a thermal component that was responsible, that was originating what we call the jet cocoon emission. So actually an emission that originates from the propagation of a jet inside the stellar layers of the progenitor star of the GRB. And actually another heritage that I got from my years as a PhD student was indeed the spectral, the optical spectral analysis. Actually, we modeled the spectral emission of the supernova as well as the cocoon using a spectral synthesis model called TARDIS that is capable to model indeed the evolution, assuming some abundance composition, density distribution, and homologous expansion of the supernova ejecta. And we demonstrate in this initial lecture that we indeed observe the cocoon in the very first phases of this GRB. And then we also have observed another event, that an off-axis GRB after the 171205 that is not related to any gamma ray burst, detected gamma ray burst, but we demonstrate with the analysis of the X-ray that I learned during my PhD years that actually the X-ray emission that was detected only 3 days after the core collapse of the supernova, or 3 days, yeah, was due to an off-axis afterglow observed, that off-axis GRB afterglow associated with this supernova, but we didn't detect the gamma ray component because indeed the jet was not pointing along our line of sight. Later days, in my last years at La Sapienza, I also developed a new research line, thanks to mainly to the support of Professor Ruffini, that was dedicated to the observation and search for narrow absorption lines, in particular lithium, in the outbursts of nova ejecta. And in 2015, actually, we published an important paper where we have discovered for the first time the presence of lithium in the ejecta of a classical nova that was detected to 1.5 years before. And our results, the yield of lithium inferred from our analysis, can completely explain the overabundance of lithium observed in young stellar population. So in principle, we, for the first time, we confirmed that nova could be the responsible of the unexplained at the epoch overabundance of lithium in young stellar population. And actually, what I learned during this year been applied to other, well, we have, as mentioned before, we started a new research line, a program at ISO telescope and Autolitho telescope to observe novae. And actually, thanks to the collaboration that I started with US colleagues and also other Italian colleagues, our data and our analysis supported this new scenario for classical novae, a two ejection mechanism where we have a first lower ejection followed by a fast wind and faster wind-like ejection that can interact with slower ejection, emitting gamma rays that have been observed in nova. Indeed, one of the main discoveries of the Fermi detector was the detection of gamma rays from classical nova. And our observation, spectral observation, combined with the gamma ray data analysis, have confirmed indeed the presence of additional component that can explain this gamma ray, very high energetic gamma ray emission observed from classical nova. Now, present and the future, yeah, because Professor Ruffini is a real machine for doing science. I remember, actually, we are still in touch. We are still proposing projects. Ruffini always calls me in the weekend when it's quite hard to answer because it's the only time that I have free. But, you know, as astronomer, we work also during the weekend. And in one of these weekends, I proposed to Ruffini the idea of use these PNRR Italian grants for the construction of an astronomical observatory in South Italy. And this is a project that we have submitted to the ministry, still waiting for the approval. And the project is very similar to another observatory that we have built thanks to European grants in 2016 that we opened the observatory in Algeria. And we are observing GRBs. We have published also a Nature paper with the data from this 50-centimeter telescope. Actually, we have proposed a 90-centimeter telescope to observe not only high energy transient, but also supernovae, searching for off-axis GRB, using space and monitoring space debris. And this telescope is in line with what I'm currently doing here. We got some grant to refurbish the Danish telescope, that is a telescope in La Silla in Chile, that should do a sort of real-time spectroscopy for LSST. Actually, the LSST is very close as a location to La Silla, and we are almost done. We have built a sort of pipeline that from the alerts that will come from LSST, we will do a selection for the best candidate that satisfies some filter. For example, we are looking for off-axis afterglow or rapidly decaying sources like GRB afterglow that are not being detected by satellites, and now we have discovered a lot of these events. And once we got these best list of candidates, we will interact directly with this telescope and provide data the same night of their discovery. I also have proposed this to Italy for the LSST in-kind contribution, what was not accepted. Denmark accepted, but this is something that we plan to do with Ruffini. So this is the present and the future. And I would like to congratulate again with Professor Ruffini at Majora. And it has been a pleasure. Well, as one of your former collaborators was used to say, I would like to repeat, more than the pleasure was an honor.
Yes, thank you
very
so
much
much.
again, Professor.
Okay, I am going to close this maratona, started from 8 o'clock in the morning every day from China, Korea, and China again, with my first student from China, which is Gao Jiangong, which we found him and he introduced this morning early from China. And then we went on, and we will put all this material at disposal because we had a very exciting, scientifically exciting point. But let me just say a few words. Before, and a statement. First of all, I thank everybody. Second, we are in a very dramatic situation in science. Dramatic. Before leaving for this meeting, I decided to write a letter to the only physicist who is a minister, Cingolani. The people interested, I will send you the letter. We are, this is the second point, we are close to one of the greatest mistakes in science, which we have proven. Professor Damour wanted to speak about the binary black hole emitting gravitational wave. Thibault was my best student. And I insisted not to speak about that because it will be terrible for his career, because that work is totally wrong. And I convinced him to speak about another paper which we wrote together, and I inspired. And is the work on the binary pulsar, which was fantastically proven correct. We wrote that in the French Academy in '74 by Lechner in French, because it was very urgent as soon the binary pulsar were discovered. And finally, Michael Kramer has obtained the evidence that the fact we postulate with Thibault was indeed correct, and now is the most accurate test of general relativity. Most accurate. We started, Kramer showed, and this is the new record of general relativity validation. But I was happy to remind Thibault. Thibault is a fantastic mathematician. I don't know any better mathematician than him. But he's a mathematician. And the work he did were inspired by me. They were co-author. I am a physicist, I'm not a mathematician. And I want to explain now to everybody, I did already today, that there is a colossal physical mistake in all this topic of gravitational waves, but it's colossal. And I will explain to you that the fact that they make a simulation postulating the emission of gravitational wave is self-destructing, because if they compute a trajectory based on gravitational waves, that trajectory can only emit gravitational wave. And therefore, there is no way that electromagnetic radiation or ultra radiation could be emitted. The system is totally nonsense. And this was created by a person who wrote a book on gravity, but that book of gravity, gravitation, has only to do with gravity and not with the other interactions. And this is one of the biggest mistake in science. But as usual, I don't look for applause or convincing people. But Galileo said that even a person that is not loquacious, but is on the right of reality, he will win. I will need all your, not your support, your interest in understanding my statement and making it will be clear to all of you that the statements are absolutely correct and there is no way out. And this has been one of the greatest mistakes in history. And finally, I close. We discover the black holes, we see the black holes, we meet the black holes, we observe them, and we are ready to show you the new physics of black holes we just started. I hope to have a new satellite looking at self-similarity and at structure of 10⁻14 seconds, because the new science is in the heart of the black hole, in the prompt radiation, which has jetted emission of 150 gamma factor. And it's fantastic to be here. Somebody's helping us. He's helping to have Tzviti Piran to explain how his work was very fundamental, but to be duly interpreted. And Marco Tavani was the first one to say, oh, but this structure you're speaking is just the jets. Yes, not one jet. There are jets on every 10⁻14 seconds. Science is the most exciting field, and astrophysics especially, in the human knowledge. I thank you all to participate in my 80th birthday, and I feel very happy that I had a small action on my body this morning that gave me back a lot of energy. I am very well now. Thank you to everybody.
Happy birthday to you.
Grazie Marco, poi ci risentiamo. È molto urgente, perché è rivoluzionario. Ciao.
Bye. Ciao.
Grazie to everybody, and grazie especially to Mimosa, who came here from the beautiful Adriatic world of Albania. She did come purposely, and we look forward to have Albania join ICRANET soon. We need more people in ICRANET, more country in ICRANET. And she has been ideal, and please come all to sign the wall of Villaratti. It's beautiful. You agree? It's very beautiful?
Yes.
Yes, okay. Okay.
Okay, Hemo. Thank you, Hemo. Bye-bye.
Remo.
Bye.
See you soon.
Thank you, Remo. Bye-bye.
Bye.
Bye-bye, Remo.
Bye.
Bye-bye. Bye-bye, Remo.
Bye. Bye, Cesar.
Hope to see you soon.
Yes. I
Hope to see you soon.
My statements.
Bye, Remo.
Bye. Bye.
Auguri, tantissimi auguri. Bye bye.
Auguri, auguri.
Bye,
Ci
everybody
vediamo.
is here.
Ci vediamo in Brasile.
Thanks. Good.
Bye bye.